Hi, Eduardo. I think you were just saying something, but I had my headset turned off. Now it should be on.
No problem. Yeah, I was just checking the sound. Can you hear me okay?
Yeah, I can hear you now.
Okay,
Perfect.
thank you. I see Nate is there, so we have plenty of time. We just wait for everybody, right? I was making sure that that the streaming was working and everything was ready. Hello, everyone. Good morning, afternoon, or evening. So we're going to start the fourth day of the workshop. As you saw in the usual daily email, there's quite a few interesting presentations today. I'm actually going to start with a couple of presentations on a very hot topic and very contemporary topic, which is differential programming, and we're very happy to have Nathan to discuss that and introduce everybody to the topic. So I see you, Nathan, already. Can you hear me okay?
I can hear you fine. Same question to you.
Yeah, perfect. So, well, the floor is yours, or the screen is yours then.
And the screen is mine. Thank you very much. Okay, awesome. Thank you, Eduardo. Okay, so I will quickly allow my screen to become your screen. There we go. Let's go back a slide. I will be giving a tutorial today on differentiable analysis, but I guess it's a bit of, as Eduardo said, it's a bit of a hot topic, bit of an emerging paradigm. So I am going to give you some slides first, and then we're going to jump into some code after the fact. I hope that works for you guys. So I'm just going to jump straight into it. We'll get started on the conceptual side of this talk and tutorial. So I'll be covering two software libraries today, which have like a dependency relationship with the arrow to the left. So there's this library called Relaxed, which is basically aiming to provide these differentiable building blocks that we can use to build these full workflows that I'll talk about today. And then there's the Neos library and method. It's unclear where one starts and the other ends. The Python package exists basically to facilitate the type of workflow that, if you're familiar with it, at least the Neos paradigm talks about. And it's built using Relaxed. So that's the software we're going to cover today. And that's how it's related to each other. And this is the repository that I will be using today. It's also linked in the Indico, if I'm not mistaken. So if you want to follow along, you can do it there. There's also a binder link if you want to actually execute stuff. But okay, I promised you some conceptual stuff. So let's go there straight away. I'm going to talk to you about how do neural networks learn, which you may be wondering, why am I telling you about that? It will be clear very soon, don't worry. Machine learning is in this talk. We have all the buzzwords. So a neural network, as is presented to most people, is this ball and stick diagram, which I've told people many a time I'm not a massive fan of. I think it kind of obscures a bit of the details away. But the ball and sticks can basically be thought of as some parameter vector phi, which is basically the stuff we want to optimize. It's like the free parameters. That's where like the learning information goes. And then the actual like layout of the ball and sticks is the architecture. And it basically refers to how am I going to combine those parameters with my data to produce maybe some sensible result. And then in practice, the balls basically are a location scale transform of the data with some weights and biases, which are the parameters they are phi together. And then we apply some activation function, which is just some way to make the location scale transform bendy, because then we can model curves instead of just straight lines. And the gray lines are data in, data out. So that's a neural network. And then you might say, okay, well, how does this thing learn? Because it will produce a result. The fact that we have one ball at the end there means we'll get a single number as the output of whatever neural network this is. I guess there are 4 inputs. Maybe it's like a 4 vector or something. So how do we tell the network that it's doing well? Well, we need some kind of feedback mechanism from the result to the phi I if we're doing this in an iterative way, and that is usually it's usually achieved by the existence of this objective function, which is also called the loss, because generally it's a quantity that is meant to measure how good we're doing. You can think about, I don't know, like first place, because it's the lowest number, but also the best result. And the reason why lowest is better is because the literature on optimization has tended to gear itself towards minimization as opposed to maximization. I think it's an easier problem in some way. So yeah, this is great. So okay, we have an objective. Now how do we update the phi I with some minimization update rule? Well, what I propose to you is this this famous learning algorithm called gradient descent. And how does gradient descent work? Well, one iteration of gradient descent, at least in its like, non-intelligent, super basic form, is you take your current phi I, and then you subtract the gradient of, say, this entire construct as a workflow from data and parameters to objective. So data and parameters go in a scalar comes out, and we say, okay, we subtract the gradient of that whole thing from our phi. And you might think, well, I don't really understand that. Why is that a useful construct? Well, if you look at this beautifully drawn artistic diagram on the bottom right, where we're a ball rolling downhill in parameter space. So the x-axis here would be like the phi I, and the y-axis would be the objective, and we want to get to the bottom of the curve, but we can't see the whole curve because that would mean we've scanned the whole space. So we want to know how to get to the bottom, and in the absence of gravity, the way we can travel is by learning where the slope is and moving kind of against the direction of the slope, because if the slope's going uphill, we want to go down. And that's why there's a minus sign there, because we're just going in the opposite direction to the gradient. And okay, so that's gradient descent. But one thing I will say is that we don't actually need neural networks to do this gradient descent method at all. It's just where it's most commonly used. For example, here is the same workflow, but we replaced the neural network with a straight line. I guess technically I said we had a 4D input space, so maybe this is less descriptive, but maybe it's a 4D plane. And on one side of one region of the plane, we say, oh, this region is the signal region. If data falls there, we say it's signal. And if things fall on the right-hand side, we say, okay, well, that is background. And then we can use that to compute a result, like it's either one side or the other, or maybe it's some continuous version of that. And then we can calculate an objective in the same way, because assuming we produce a result in the same form, like a single number, on the left or on the right, I guess. And then we could still do this whole thing, because the only real restriction from doing this method was to calculate that gradient, right? And the gradient of the workflow is a tractable quantity if every step within the workflow is differentiable. And so the straight parameters of a straight line are differentiable, quite clearly. Like if we differentiate with respect to the phi I, which is the m and c, we're going to get like just x, or we're going to get 1. So I think if we can calculate the gradients by hand, we can maybe trust a computer to do that too. And yeah, so this is entirely possible. And so this is one of the two ideas that I want to present to you today, is that using gradient descent, we can optimize any workflow parameters. Don't have to be in neural network weights. It could be a straight line, for example, with respect to any goal, if the full workflow is differentiable. And I'm going to show you a couple HEP-like examples of this. I'm going to lay out a pipeline. We'll talk more specifically about the pipeline later, but just to put some things in your brain. We could imagine maybe if we're doing a high energy physics analysis, we start out with some data, including some, signal background contributions and maybe some systematic variations. We might pipe it through a neural network, but what I actually want you to visualize here is just any kind of like abstract set of like analysis configuration steps. This could be like a cut flow or binning, or like, I don't know, maybe you're doing some kind of calibration and within all this, but all of that might have free parameters that are floating that you might want to optimize with respect to some goal. A neural network is just an example of that. From there, we're going to produce some kind of one-dimensional, at least typically, we'll produce a one-dimensional summary statistic of the data, which involves a histogramming step. And then we do kind of like the typical things to set limits or get a p-value. We'll construct a likelihood model. We'll go and Google the asymptotics paper for the millionth time to find out which test statistic we should use. We'll do the hypothesis test and maybe get, like in Atlas, we use the CLS value, which is just a modified p-value where you divide by a p-value from testing against the background only hypotheses. And then maybe we want to do something like this, where we back propagate through the whole chain. We're going to get to this later, but what I would like to just present to you as an idea is that if we wanted to do this to basically get the gradient of that whole workflow, we'd have to get the gradient of every individual step. And you might be asking, well, how do we get the gradient of, like, I don't know, like likelihood building, right? That's like weird. I can't write that down on a piece of paper. But in practice, this is all code, right? This is all computer code, and there are ways to differentiate computer programs. And you might have seen some of these names before, JAX, PyTorch, TensorFlow. These are the machine learning libraries that we all know and love, or at least know. And the real thing that these libraries do is they're frameworks for something called automatic differentiation. And just to give you a quick explanation of what that means is, if you can imagine like NumPy, for example. NumPy is a set of operations that are like, really frequently used to do linear algebra, like, exponentiation, sum, I don't know, like mesh creation, all sorts of fun stuff. But it ultimately is just like, it's a set of operations that have mostly known gradients, right? Like, if you want to take the gradient of like a sum, we know we just take the gradient of all the individual terms. If you want to take a gradient of a product, we break it up with the product rule. And then, log x is 1 over x and et cetera, et cetera. So we know these have derivatives, but how do we actually calculate them, especially in an automatic way? And so the bullet isn't actually on the slide, but there are systems that you can basically make a wrapper around like your numerical programming library. And for every operation, you can just record the derivative that you know already. And then when you when you run a program, so when you execute it at runtime, you can then just have a look at all the different operations you did, like in a row or in a DAG or whatever. And then you can take all the gradients that you put in and then basically compose them via the chain rule as a product, and then you're done. And it's, I'm simplifying it to some degree, but, there exist efficient ways to do this. And the great thing about automatic differentiation is that it's not only efficient, it's exact, because we're using these, these analytical primitive derivatives that we put in ourselves because we think we're okay at mathematics. So that's just to tell you like where gradients are coming from. But then you might say, okay, well, let's just put all our analysis code in PyTorch and optimize the whole thing, right? Well, that doesn't quite work because indeed there are some operations that are not a priori differentiable, right? Like here is a very discrete boy on the right-hand side, awfully behaved. If we move the rug of data beneath a histogram and we want to know how like the bin heights vary as we do that, events are going to stay in the bin they're in as you move the data, because remember, the gradients are like the language of small changes. So I'm thinking if I change X a small amount, how are the bin heights going to change? And you will think, well, they're either going to, the event will stay in the bin so that it won't move at all, or it will hop over and then the bins on either side will migrate up and down in this very discontinuous way. So that's not a thing we can like get gradients with respect to very easily. And then this is this idea of relaxation. And that's like it's a term used in the machine learning literature to mean let's take an operation and approximate it with like maybe a continuous version of that operation such that we can take the gradient across it. And let's look a little bit further into this. So here's just an equation showing that like not all these things are differentiable and we can change it. So here's an animation of exactly what I just described. We're shifting the data underneath the histogram and we're seeing how the bin heights are changing. And we can see that basically this isn't well behaved at all. And we might want to change something about that. So something that we did, for example, here's like the first relaxation that I'm showing you, is where we replaced the histogramming process with a kernel density estimate. And a kernel density estimate, for those who haven't heard of it, is basically you select a kernel function. The most common one is like the standard normal distribution. So you have a Gaussian, right? And then so for every data point, you put a Gaussian on the data point, and then you say, okay, well, my probability distribution then is just like the average of all the Gaussians. So you say, I evaluate like at x equals 5. I then get the Gaussian at each data point, evaluate that at x equals 5, and then I just average the results. And if you do that, you get this pretty like smooth envelope over your data. And what you can do then from, because this is a smooth envelope, right? How do we get a histogram? What you can do is, because, in this case, we have a probability density function. It's just a Gaussian mixture. And that has like a known and tractable cumulative density function. And then you can say, okay, well, the area under the curve in a specific region as defined by a bin is the the cumulative density function, up to the right bin edge minus the same thing to the left bin edge. And then you have the area just in that region. And so that's how we construct these differentiable histograms. And that'll be one of the first things we'll go into. There's some other stuff that we'll talk about later, including cuts, differentiable likelihood building, and also differentiable fitting. So that's the first part of the conceptual presentation. I'm now going to show you some degree of that in code. And so I'll be, again, using this differentiable analysis examples repository that I've created. And if you click there's a binder link there. And if you click that, if you want to run it, you can just watch me. You will get a server connection error. No, you will get some instance, and you'll be able to see all the notebooks. Some of the stuff, like some of the animations might not work, but I'll be showing you them anyway. So, and if you really want to make it yourself, you can ask me after the fact. I will quickly pause here though, just in case there are any questions. I do have the Slido open in front of me, and I don't see anything, but someone can correct me if I have the wrong version open.
No questions so far.
Okay, fantastic. So let's jump into the code then. So I was telling you about differentiable histograms. So let's look at that first. So a differentiable histogram, we define it via a kernel density estimate. I have like a link there which talks in more detail about the implementation. It's basically the same thing I just talked about. But through these notebooks, I'm basically going to be showing you the images mainly, and I'll highlight the parts of the code that are doing the magic. So the text is mainly for you to go back and look at later. So let's have a look. Okay, yeah. So the first thing we're going to do is we're going to run the first two cells of this notebook to get this beautiful thing, because I want to show you. Well, I need to get my matplotlib settings to work. There you go, a little bit bigger now. Okay. So here is a example of a histogram of some data compared to, we call this the KDE histogram. We call it a BKDE, B standing for bind. And there's this parameter I didn't tell you about actually. So remember how I said we put a Gaussian at every data point. So I've specified the center of that Gaussian, but I didn't specify to you the width of the Gaussian. And that's because all the widths are controlled at the same time with this global parameter you can set. It's called the bandwidth. And we're going to see what happens to both the kernel density estimate and the histogram as we vary the bandwidth. So the first thing you'll notice actually is that the curves are a little bit off. The histogram doesn't match the actual histogram, so aren't we doing a bad job? And I say, okay, well, I'm going to reduce the bandwidth a bit. And we see what happens. Okay, we're doing a lot better now. And maybe it looks like it's actually going to converge. So I'm going to drag it all the way to the left. And whoa, what's going on there? Everything got a bit crazy. Now, if you look closely, you'll see that the dotted orange line, or I guess it's not the dotted line, it's the solid line. It is actually tracing over the histogram perfectly. If I take it slightly less bandwidth or more bandwidth, you'll see that that's true. But why is it so, why is the kernel density estimate so jagged? Well, that's because if we have a Gaussian at every data point and we shrink the width to 0, then we have a bunch of basically delta functions at every point. And if we integrate over those, we're going to be counting events, because, it's just a contribution of 1 for every event. So while the envelope of the function looks horrible, we do recover a standard histogram. Now you might be asking, well, if we want a standard histogram, we can use a histogram, right? Well, what's this for? Well, as I said, the thing we want is we want the gradient of the heights of these bins, and I'll give you an example below where we can use that. You know what? Let's just do that right now. So we're going to optimize through a histogram, and through just means that we're taking the gradient of a quantity involving the histogram yield, and so gradients start before it, with some quantity like the data which we move, and then the bin height will move, and then the gradient goes across that process. And so this is a bit of a confounded optimization problem just for demonstration purposes. So we're saying if we have many events xi, what is the value delta such that the peak of the histogram of xi plus delta, so we're making a histogram of xi, and then we're shifting all of the data by some constant factor, and we're saying what happens when the peak of that histogram is at some desired target value. It's completely a toy problem, but the reason why we might need this differentiable histogram is because, well, if we set this up with gradient descent, like I talked about, to optimize this delta term, we're going to have this mean squared error, which I'm highlighting there in blue. So it's the mean of the histogram, just like I talked about, after we've shifted the data, and then we say minus the target value. So if you want our data to, our histogram to have a mean of 3, we say, okay, t equals 3 in the loss term, and then we will take the gradient of this loss, which is obviously going to be 0 when the mean equals t, and then we try and minimize it. And so that's what I do. If you run these cells, we get to do some gradient descent fun. You'll see the value of delta moving, and I guess there's a video here that I cannot hide. And we see what happens when this system learns. So the maroon line you can see moving from left to right. That's the current mean of the histogram, and the histogram itself is moving left to right as we shift the delta. And we wouldn't have been able to do this if we didn't have differentiable histograms. I'm actually curious, so I'm going to go into the code and I'm going to change. So I told you I'd highlight the interesting parts of the code. Right here is like the shift histogram function, which is, where we shift the inputs and make a histogram of them. And you notice here we're using the first version of relaxed. So instead of like numpy.histogram, I'm using relaxed.hist. And I'm also providing my inputs. I'm providing my bins in the numpy style. And then I'm also providing this bandwidth term, which is controlling that, degree of approximation. So if I comment this out and I write soft counts equals, let's do numpy dot histogram of what was it, shifted inputs, and then bins equals bins. I guess what I should actually do is make sure we're using Jack's version of NumPy, which I think we are, or maybe we're not. It doesn't matter. And then what happens if I try and execute the same thing? It's going to start failing and complaining. Yeah, okay. So it's complaining because we used regular NumPy and we need everything to be in our automatic differentiation framework. So what I will just do to get around that is I will say import jax.numpy as np, and then we'll do exactly the same thing again. And we have an error again. It's not the error I wanted to show you. The error that we should have gotten is like the gradients are 0. I think there's maybe some other stuff in here that doesn't work. But anyway, I didn't test this beforehand. But the point is that it's not going to work through whatever mechanism you decide to show. So the last thing I'm going to try is just doing this term. So everything else should be normal NumPy. No, it still doesn't work. Okay, great. It doesn't work, but that's what I wanted to show you, is that we need differentiable histograms in order to be able to do this optimization problem. And if histograms wasn't your, didn't take your fancy, I'm going to show you basically the same principle again, but through a much more familiar analysis challenge instead of some abstract problem. And we're going to be optimizing a cut value to get the best significance. And so the first thing we do here is just some data generation. It's all toy, not necessarily important. Here's the resulting plot. So we have some exponentially falling background with a signal sitting on top of it. And we might say, oh, let's make a cut on this value X and see if we can get better significance. And I should have a Jupyter widget open. I got to run the cells in order. That would drastically help my situation. I think that did the trick. There we go. Okay. So once again, you guys hate this as well. When you update matplotlib settings inline in a Jupyter notebook, I have to run the cell twice. I should just use like a matplotlib.rc file. Anyway, so here is an example of varying the cut value and seeing the significance we get with a particular cut. So if I put my cut all the way to the right, we have a significance of 0.03. I don't think Atlas will publish that. So I'm going to say, right, let me dial it back a bit, see how much of the orange I can keep. So if I do like that, I'm keeping most of the orange. That's, oh, well, 4.8 sigma. We're nearly there. We're nearly there to the grant application. I'll squeeze it to the right. I think that's about the best we can do. 5 sigma, I'll take it. And I'm sitting here enjoying my new tenure track position. So fantastic. So that's, typical. That's what we'd like to do in an analysis, just do it by hand. But maybe there's a more intelligent way to do this. Let's have a look. Oh, I do see a quick question that I'll quickly answer. So it's about the automatic differentiation frameworks that I showed, because I talked a little bit about JAX in the previous notebook. And the question says, out of TensorFlow, PyTorch, and JAX, which is the go-to for automatic differentiation in terms of performance? The short answer is whatever works with your current setup. And the long answer is for GPUs, basically JAX and PyTorch are the way to go. If you want to do standard machine learning stuff, PyTorch is way more mature in terms of an ecosystem. If you want to do like researchy type stuff, like I'm showing you here, then JAX is a little bit more flexible for that. So yeah, that's the answer to that. Let's go on with the cut example. So, as I just showed you, we can get the significance like optimized pretty well by just scanning over the values of the cut and seeing what happens. We do the same thing here. So here's a plot of the significance as we vary the cut value and the optimal cut. I think that's about what we had before. Yeah, so we came up with the cut of 1.5. The optimal cut is 1.54, and then you get the best significance there. But now what I'm going to do is I'm going to introduce you a relaxed version of a cut. And we're going to do gradient descent to optimize it automatically, because maybe in a real analysis, you'll have many cuts and you can't do this fun scrolly thing for every single one of them. So a sigmoid function has the form here, if you can see it on the right. So it's 1 over 1 plus e to the minus x. And I'll show you basically what that looks like below after I run this out. Cut values is not defined. Why are we trying to do that?
Nathan, just to say you've got a couple of minutes more or less, okay?
A couple of minutes?
Yeah, flies. Well, a few more, but not 10.
Okay. I thought it was a 45-minute slot, but okay. We're pretty much towards the end anyway. Sorry,
my fault. Indeed, yeah, you have the full hour, so
it's a 1 hour slot, right? I was like, that's
yeah,
I have like 3 more notebooks to go through.
no, I'm just sorry.
Okay. Oh, you scared me there for a second. All right. Okay, now I feel like I have enough time to run my cells after that brief scare. There we go. Okay, beautiful. This is exactly what I wanted to show you. So I'll draw your eyes to the plot on the left here, where we have a plot of the weight applied at X from both a hard cut and a sigmoid cut. So what I mean by a hard cut is that we're just saying keep all the values bigger than the cut value. So this is a cut at 2, and I'm saying, okay, that's equivalent to applying a weight of 0 at every value less than 2 and a weight of 1 at every value bigger than 2. And you can imagine then that there's a pretty easy way to think about this in a continuous way. Well, you say, okay, if I bend this slope a bit, like this orange line, and that's the formula I showed you above, we're plotting 1 over 1 plus e to the minus x with a slope parameter multiplying the x. And I can show you what happens actually as we vary that slope. So you can see as we go from left to right, the slope changes, and then you have a plot on the right of how the data itself changes. So if we go all the way to the left, the right, where we have like a maximum slope, you can see that the data after the cut from the hard cut and the soft cut is the same. And if we reduce the slope a little bit, basically making it more smooth, which in your mind you can think about as less variance in the gradients, because if you have a really steep function, you're going to get like a lot of variance as you try and take the gradient across the cut value. And you can see we're introducing a bit more of an approximation, right? So we're actually getting some leakage to the left of the cut. And that is just an artifact of the fact that we're changing the slope to be non-zero on the left-hand side of the cut value. But what that will do, though, is give us a much smoother gradient estimate, and then we'll be able to use it in optimization. And I'll show you in the next plot, actually, that it might not matter so much that we're introducing a bit of approximation, because in the real analysis, we can take the cut values we get from the optimization and then use them as the cut value for the hard versions of all the operations. But I'll show you that here below. So here's the scan of the significance with the hard cut there in blue, and then the soft cut there in orange. And you can see, okay, well, clearly there's some approximation going on, right? But actually, if you look at the location of the maxima, we're basically in the same place. It's about 1.5. And that's the only important part when we're doing this. We're introducing this notion of approximation, because of course we'd like the slope of the sigmoid to be as close to maximum as possible. At some point we won't be able to train, though, when we do that. But the really important thing is that if we just find the place where we have the best significance, that will hopefully be approximately true for both the soft and the hard operations. And I don't know if I might have actually missed the step when I meant to define this, but by hard and soft operations, I mean the original operation, like the cut with no relaxation, and the soft cut is what is the sigmoid I'm talking about. So it's been made relaxed in some way. And so that's something to keep in mind as I show you the next step. And I will just quickly flash the API of what I just showed. So in this function here, you can see that there's this relax.cut function being called, and it's being called on the data with a cut value, and then also a slope value. So you'll notice there's a pattern here, that everything we're calling is exactly the same as maybe like we'd expect from NumPy or whatever, but we're just adding an extra parameter that's controlling the amount of approximation that we have. So from an API perspective, I think it's pretty nice. Now, what happens if we do this whole thing with gradient descent? So I'm going to say, like I've been talking about, right? If we want to do this optimization, we need to have a metric to minimize. And so instead of having I have like a helper function here to calculate the Asimov significance. And instead of optimizing that, I will just optimize 1 over that, and that will minimize that, therefore maximizing the significance. I've just seen an extra question. So how are the entries selected with the sigmoid? Are they weighted? So indeed, it's exactly what I just showed. Great thing to point out, though, because like I said, so I guess the thing that's different is that when you apply a hard cut, you're actually going to do in code, you're going to write something like, X indexed at X bigger than the cut value, right? So you're actually going to just lose all the entries that you didn't care about. But the difference here, I guess, is that you just have a set of weights instead. So it's exactly this. It's weighted by 1 at this data far from the cut, and then near the cut is where we start to reduce those weights, and then at the end of it we're at 0 again. But yeah, so we have to save these weights basically, and we should be able to drop the ones that are identically 0 without suffering in this gradient paradigm. But yeah, that's how it works. You're exactly right. So yeah, the thing about this is also a great question. How can you be sure that the location of the maxima is the same? You don't know. But that's why you do these scans, which you can't always do. I guess like this one, but you can say a histogram has no approximation at bandwidth equals 0. And it was very clear that as we drag that bandwidth from left to right, that we introduced some approximation that was very clear, how much. And maybe you have some really unstable situation where that suddenly creates this massive discrepancy between the position of the true maxima and the approximated maxima. But I think that because these notions are tunable, you can at least say it's probably good enough to some degree. And then, there's no guarantee though. You're absolutely right. But I would say it's at least something you can diagnose because you can tune the amount of approximation, and then you can always run it with everything set to no approximation, and then you can see if the maxima is, or like at least your result is pretty good. But yeah, you can't know for sure the location of the true maxima in practice, and I think that's like something you kind of have to live with. And then I'll just do one more question before I keep going on. So is it possible to make the smooth cut increasingly harder throughout optimization, or there are issues? Now that's a fantastic question, because that's something that I've wanted to try for a bit, and I think that it would work. So this is something that, so just to explain the idea is that you can imagine that as we get closer to like a minimum in like your loss landscape, maybe then you can have some additional approximation, because like the steps you are going to be taking are not going to be as big. So maybe if we make things a little less approximate and we make this a little bit more like a bit of a crazier loss landscape, because we're only moving in small jumps, maybe we can actually move in a little small jump to somewhere, that we actually want to be. So it's a great idea. And I haven't tested this properly yet. And I don't think there would be issues in practice beyond like trying to make sure that the issues you could arise with are like suddenly your gradients do go crazy and your whole training crashes. And so that would be something you'd have to monitor. But it's a great question. Great idea. So, okay, I'm going to go a little further and then we can come back to some more questions. Let's see. I left you here where we compared the significance of the soft and the hard cut, and I said that you can see the cut value position is pretty similar, and this is all the code you need to like actually optimize this system, right? So like I said, we're optimizing 1 over the Asimov significance, and we have this really neat like minimization API from JAX-opt, which is a optimization library written in JAX. We need to keep everything in JAX to make sure the gradient information is propagated. That's why I'm doing that. But they also have like SciPy solvers and stuff as well. So it's you can use something you're more familiar with, but here we're just using gradient descent. And this cell, if I hit enter, like it runs. I need to run the whole notebook, so I'm just gonna spam shift enter to make sure we have like some idea of coherence. Okay, great. So that cell runs in about, it's like half a second, and we already find like a cut value of 1.35. And you can see the significance of that cut is 5.17, and the best significance we could have ever got is 5.19, and I'd say that's pretty good. And the significance there is calculated with no approximations, just like I said. We're taking that value and using it in the hard version of this calculation. And yeah, I guess a quick nod to Alex Ald, who's definitely among us somewhere, because this at least explanation is based on a notebook you made. So thank you for that. Okay, I'll just quickly check the questions one more time. Okay, so I only missed one actually. Just asking, isn't sigmoid usually used for classification algorithms? Yeah, exactly. So a sigmoid output is used in neural networks where you want to have a bunch of different output nodes, and then you use the sigmoid to basically fill those with different like probabilities. But here's just showing you another example where it can be used to approximate the step function. There's no real restriction to the way in which you use these things. So yeah, the answer is correct, and it is both. So the last thing I'll show you while we're in this paradigm, I hope you're getting like the message that we can do like using these differentiable versions of operations. We can use gradient descent to solve some typical problems we have in high energy physics. I'm going to run all the cells because I don't want to have any more errors and slow us down any further. So we're in the same paradigm. We have a signal back on top of some background, and what we're doing here instead is I'm going to propose a different analysis problem and say, okay, I've shown you some binning, but say we don't know what the ideal binning is to get the best significance. And this is again something we can optimize if we have a differentiable histogram, because we can, as the bin edges move, things will migrate again in a normal histogram, but in a BKDE, in this relaxed histogram, the bin heights will vary smoothly. And why do we care? Well, the bin heights, as I said before, they are used to calculate the significance, right? Because you need the number of events in the bin from signal and the number of events from background. So if those are not smoothly defined, then we can't calculate the gradient. So I'm going to be showing you an example of differentiable binning optimization using a differentiable histogram. So I'm just going to scroll through and see if there's anything new. I think it's the same sort of thing. So I'm here's the pipeline to calculate the significance, where basically there's a couple of lines here that make sure like the bins don't overlap. But then, this loss it's exactly the same as before. We make a histogram of the signal with the new bins and the histogram of the background with the new bins with some bandwidth that we decide to pick. And then we optimize again 1 over the Asimov significance. It could have been minus the Asimov significance or whatever, as long as down means better. And I think let's see. So yep. Oh, and here's some results. Okay. So, sorry, the legends are kind of a bit intrusive. Okay. What I'm going to do is I'm going to remove the legend, and you're going to trust me that orange is signal and blue is background. Okay. That's a trust thing we're going to have together. There we go. Okay, fantastic. So here are some example binnings of the data I showed you before, where we have in the title of each plot, we have the number of bins that we need to keep fixed because, we can't have 2.5 bins. If we could, then maybe we could do this kind of smooth optimization. But I haven't thought of a good way to do that yet. So, and I think it's pretty cool. It's like, the shapes are pretty funky, but from a stat-only significance perspective, these are actually looking not so bad for histograms. And one thing that I really like, actually, it's a little bit subtle, but you can see that the axes, the axes aren't actually starting at 0, they're starting at like 1. And that's because the bin edge on the far left is actually being dragged to the right. So it's actually learning to make a cut. Because there's only really, if we go back to like the first plot, there's only really background, less than 1. And there's actually a bit of leakage past 0. That's just because I generated with a normal distribution. It's not physical, don't worry about it. But all of the binnings learn to like cut away that bit of background that wasn't really doing anything. So I think that's a pretty cute application. And, we're discovering all of these signal processes, which is great. And okay, I think I have the same thing, but animated. Yeah, here we go. So we can see what happens to the binning like during the optimization. And then I guess here you can see that cut happening actually. Yeah, there you go. So the bins are shrinking. It's a little bit slow, but yeah, we'll get there. So it's saying, okay, I'm going to really shrink this because I'm not losing any signal, and I get to keep all the keep removing the background in that bin. And yeah, like the signal to background ratio is going up pretty much all the time. It's doing this weird thing right now where it goes down for a bit, but then it recovers and says, okay, let's increase the significance again. But yeah, just to show you that this is possible. And if we look at the code for this, again, we're just using this the loss function, the 1 over the significance, the optact solver from JAXOPT, and then there's just a bit of boilerplate here to like do some plotting, but I think it's reasonably clear. Like we're doing a number of steps, and we're doing for I in range steps, and then we're just updating the solver. I think I saw a question here. Let's see. Okay, here we go. So why use 1 over the significance? Why then minus significance? No reason. I think minus log significance is probably the best thing to use, right? But I mean, this is a pretty toy problem. I mean, it's not gonna. We can actually, you know what? Let's just change it. Let's just do it right now. Now it's minus significance, and I'll let that run for a bit, and we can come back to it. But yeah, there's no reason at all. In practice, okay. So what happens this time? Minus significance. We can skip ahead. Yeah, it's about the same. Oh, it really full screens. That's quite fun. Okay, yeah. It seems to be doing pretty much the same thing, but yeah, no real reason for it. I don't know which one has more numerical stability. Another great question is relaxed and what I'm showing working well together, like hist and boost histogram, or the bridges needed? Bridges are needed because a relaxed histogram is a fundamentally different object from like a histogram, and they only really have utility in optimization. This is something we haven't really discussed like so much from an API perspective, and it would involve like hooking in jacks on some level to making sure the derivatives pass through. But yeah, in practice, that would be great, right? So you could use like this exactly the same API, like through all these great HEP packages we have, and you wouldn't have to like jump through these like NumPy histogram hoops. We could just use the nice hist objects. But yeah, there's no conversation there, but that's one I'd happily start. I just have no idea how to do it. There was one last question that I'll answer before I move on to the final notebook. Let's see. The max discrepancy can be quantified by checking the optimal hard cut, but what if that's computationally expensive? Exactly. So yeah, I mean, that's what I went on to say. I said that you can check the optimal hard cut, but in reality, we can't do this. But like to have something that has a tunable degree of approximation that you can, try your best to make as much like the original as possible, and then have something that is intelligently optimizing towards a minimum of that function. That's as good as you can do, in my opinion. And there are no strict guarantees. There are no theoretical guarantees, but you can definitely say that, well, the less approximation I'm using, the closer to that position I will be. And yeah, like exactly, it's computationally expensive, so you can't know, but like what method can know is my other question, because I'd rather use that if you know of that one. But okay, so that's differentiable binning optimization. I will quickly jump back to slides just to show you one last thing, because what I've just shown you there was all to do with optimizing existing problems we have in HEP with gradient descent. But now I want to give you a second thing, which is what if we can use this to get better objective functions? So for example, what makes a good observable, right? I was talking a lot about 1 over the significance minus significance, whatever, but that's this Asimov significance formula that doesn't account for background. And maybe the shape of our machine learning observable isn't actually that good when we include our systematic variations, because the observable, like the training process, has no idea about like the profiling stages we're doing when we build the likelihood function. And here's just a quote from a deep learning review that says we need to account for systematic uncertainties. So that's the next idea. Can we learn to incorporate systematics? And this is idea 2 from the previous workflow that I showed about optimizing a machine learning workflow, is that we can directly optimize the discovery significance or the CLS if you're an Atlas person. Well, they're not the same, but if we could do this, right? This is a systematic aware construct, because we are putting our systematics into the likelihood function, and then we are profiling over them when we make the profile likelihood ratio. And if we minimize the p-value of this whole thing, and this p-value, this is the thing we're reporting, right? To get our grant applications, we say it's this many sigma plus or minus whatever. And if we can optimize that thing, that is, that's what we really want to do. And how do we do that? Well, we can use a lot of the stuff that I've just shown. So if I go back a couple of slides, this thing, right? So this is exactly what I proposed to you. This is saying, okay, let's do a hypothesis test and let's optimize the result from that directly. And so you can see, to do this, we're going to need a differentiable bin summary statistic, a differentiable likelihood model, and a differentiable test statistic and hypothesis test. Now, the first one we covered already, right? We have differentiable histograms already. Differentiable likelihood modeling, what we can do for that is we can use PyHEP, which is this wonderful Python package that implements like the hist factory likelihood. And then for the test statistic, it's actually already differentiable to do like this maximum likelihood fitting, but we are using a little trick underneath the hood I don't think I have time today to talk about that, but if you ask it as a question, I can add that explanation. And so that's what we have in the last notebook. So we're going to optimize a simple 1-bit analysis that has a systematic, and we're going to show that we find the systematic aware solution and not the statistical only solution. So this is the model we're looking at here. So we're saying it's 1 bin where the signal contribution is a fixed number plus phi, some parameter phi. The background is again fixed, but it's -2 phi. So as we decrease phi, we get more background, less background, and more signal. But then we have a background uncertainty term that depends on phi squared. And just to show you what that looks like, we have another fun widget plot. So as we drag phi from left to right, the background goes down, the signal goes up. But what's this? We have this gray band of uncertainty that's going up and up and up and up and up and up and up. And this is like a pathologically constructed example to give us a case where we have like, signal to background ratio is optimal on the right-hand side. But we have background uncertainty that, we know means we're going to do less well than we think we are. This isn't just a question of amount of blue versus amount of orange. This is, there's some kind of complicated question that we're really wanting to ask, which is actually maybe we want to do something like this, right? Where we still have a good ratio, but we have a small background uncertainty as well. So here is basically in code, me calculating a p-value from this entire thing, because I said we want to make it differentiable, right? So we have a histogram, so we don't need to make that differentiable. We can just grab the yield straight away, which we're doing there. We make a model with a differentiable version of PyHEP. We calculate our Asimov data for that model. And this model, it's called uncorrelated background. It means we have one bin-wise uncorrelated systematic. I mean, there's only one bin, so uncorrelated doesn't matter. But it's just like a fixed uncertainty that, with these, with the background uncertainty there, we're basically, interpolating between the up and the down and calling that that's our continuous description of the uncertainty. And yeah, so then we actually calculate the discovery p-value. And so what we're going to do is we're going to take the derivative of this entire pipeline. And that will hopefully give us a systematic aware result. So if we scroll down a little bit to this plot, this is basically scanning over the p-values with and without the uncertainty component on the model. So if you take the gray band away, you get this, the p-value corresponding to the purple curve. And you can see that the best p-value when we have no uncertainty is to shove phi all the way to the right. Remember, where we have no uncertainty, we have high uncertainty, but we have the best signal to background ratio. When in actuality, our best results, it's somewhere like around phi = 5, and we can play with this, right? So we're kind of around phi = 5 here, and we have like a nice balance of uncertainty and signal to background ratio. And that's what we're actually looking for. And so the question is, if we run this optimization process, will we be able to find the correct minimum? And it takes about 2 seconds to run, and we get a phi that's almost exactly the optimum solution. It's exactly the same optimization API as we showed before. And if you run this more complicated thing that all it is plotting code, we get this fun animation, which I'll play from the start. So the blue point is where we're currently at in the optimization. And you can see that the blue point, which is the value of phi that we're optimizing, it's going to the, it's following exactly this blue curve that was, it's the full model, the discovery p-value that we're able to optimize with respect to. And I think this is super cool because you can see the network learns to stop where it decides, okay, that's enough, uncertainty reduction. Now I start to care more about the signal to background ratio. And if we did the same thing with Asimov significance, we'd end up all the way to the right, and we'd have a awful background uncertainty. And I think based on time, I do have one last notebook that I will just flash. If you want to do the more complicated thing that I've shown in my paper and my other presentations, this NEOS workflow, I have this, big notebook there that introduces this toy problem. And, it does the actual full optimization and shows you that we can reproduce the paper plots. And I guess the only thing that I will say about this is that there's some, based on what I've shown you, I think there's a speculation that you can just like use Neos as like a drop-in loss function, when in actuality, you need to have a detailed statistical model specification, because if you want to optimize your specific systematics to your analysis, you need to be able to describe those. And if you aren't able to, like, if you don't have like a PyHEP or like, I mean, if you don't have some likelihood function, it doesn't have to be anything to do with hist factory that involves this, process, that you can't just drop in like some Neos code and suddenly your systematics are being picked up on. It does require some more detailed physicist input in that respect. So I think that's me done. And I will now just scroll through and see if there were any questions that came up during that. Is there a risk of bias when optimizing significance in this way? I'm assuming you're talking about what I just showed, based on the time that was asked. So if we optimize significance this way, there is a bias in the, where there is approximation. So there's absolutely a bias involved when doing this process with where we're using these differentiable surrogates. But actually, in this particular example, if we use the differentiable histogram and the bandwidth was not identically 0, we have a bias, right? I mean, you can see if we even go back to that first notebook, like we're literally making a bias, right? Like the yields are not Poisson distributed. There is a bias that we are introducing in the optimization. But the result that is calculated with no approximation, so your actual analysis, that will not be biased, but your optimization will be, because you're not actually optimizing the true significance. And then if you were, then you wouldn't actually be biasing in that way. I guess it's as biased as, like your learning algorithm is biased. Let's see, did I miss anything else? I think that does it for questions on Slido. So I can say thank you very much for listening, and then I will open up to any auditory questions if there are any.
Thanks so much, Nathan. I'm sorry for the hiccup.
No, it's no problem at all. It actually took us the time with a bit of hiccuping.
No,
so,
but that was brilliant, by the way. That excellent presentation. I really enjoyed it, and personally, and I already had a few thoughts myself for some applications.
Oh, that's great. I mean, we can talk about that.
I'm pretty sure the same for many other people. So yeah, I don't know if there's any more questions or even live. Yeah, you did go through everything on Slido actually, and we still have 2 minutes, but raise your hand.
I can hover for 2 minutes.
Yeah, no.
Any burning questions? I mean, you can talk about your application if you want.
No, well, actually, it might be touched by the next presentation. So I was thinking about optimizations for in complicated amplitude analysis, where sometimes the binning in the phase space of the decays matters, and so people do this sometimes a bit semi ad hoc way, and this sounds like something that could be an application.
Yeah, for sure. I mean, what's actually quite funny is that if you scroll down in the binning notebook, I actually have all this code that tries to do like systematic aware binning, which is binning optimization. There are some hiccups because we haven't gotten the specific model here fully differentiable yet, because, like when you form a systematic, it needs to be differentiable. And I think for this model, this kind of uncorrelated systematic is, I have a PR into PyHEP, but we haven't fully worked out the details. So this didn't necessarily pan out super well, but it's like I could run the optimization, and I think that's also very interesting that we could do this kind of like, cutting and binning optimization all at once. And actually, one thing I will just quickly say, since I have like 30 extra seconds, is that this Neos notebook, if you scroll down to the like the printout of the optimization, you can see that it's also printing the bin edges. And actually the binning of the model is being optimized at the same time as the neural network. So these are being optimized at the same time. And so you could even have this with cuts as well, right? You could have a cut and a binning and a neural network, and it's all optimized at, at the same time, and it's all talking to each other. So you don't have like one thing that worked well, but if we change the cut now, the histogram is bad. And I think that's actually one of the biggest areas of promise, I think, is this joint end-to-end optimization of an entire workflow. But yeah, just wanted to flash that.
Yeah, that sounds indeed very, very interesting. Very interesting. So thank you very much again. That was brilliant.
Yep, no problem.
So we're going to continue on differential programming with Remco on the topic, but for a slightly different piece of work. So Remco, hi there.
Yeah, hi there.
Hello.
Let me share my slides.
I think you're sharing, so please go ahead.
Yeah, so hi everyone, I'm Remco, and I'm working on the CompRadiWay project, which, as Eduardo already mentioned, is a project for amplitude analysis. So we offer several Python libraries and websites that facilitate amplitude analysis. But I'm actually want to focus on a technique that we use that could be useful for more general audience that has an interest in differentiable programming. But before I go into the notebook itself, and before we look at the code, a bit of background. So as I said, I come from the world of amplitude analysis, and generally the problem that we try to tackle is that we want to know what happens in between some initial and the final state. We're interested in what kind of intermediate hadronic states could be there. So if we have this J psi decay decaying to sigma k p bar, we hypothesize that there could be 3 different kinds of subchannels. And each of these subchannels can then have several resonances of different spin and angular momenta and energies. And the challenge now is to find models that most accurately describe the distributions as we see them. Now, what's difficult in amplitude analysis is that these models are very complicated. You have several interference effects that you need to take into account. And well, on the top level, the full expression is still kind of recognizable. We have the 3 terms for the 3 subsystems here. But each of these amplitudes here, they have to be aligned to take certain spin effects into account, and you have to compute helicity angles there from the 4 momenta that you measure. And then each of these sub-amplitudes, they are also again a large sum of spin projection terms, and in turn, these ones also have certain parameterizations for the dynamics for dynamical effects. Now, as you can imagine, these kind of models, they are very sensitive to fluctuations. So you actually do not want to bin your data. You work with unbinned fits, and therefore you want to have very high performance computing so that you can quickly try out a new model and then run a new fit. So that's one side of the story. You need performance, but I want to emphasize this flexibility that you do. If you have some theoretician who says like, "Oh, could you please try out this different dynamics line shift?" You don't want to have to re-implement everything. You need this flexibility to quickly try out new things as well. So we have been thinking, how can we make this easier to do it, so that you bring the implemented code a bit closer to the theory that you are trying to implement. And 2 main ingredients that we use are these computational backends that have become available for machine learning and data science. I bundle them under the term differentiable programming. And the other is the introduction of a computer algebra system. And that gives you, well, the 2 main key ingredients that I just saw, that I just mentioned. The small consequence is that you also kind of automatically document what you're doing. So that's well, we'll see that that's a quite nice side effect. So I guess that that you've seen all these frameworks for machine learning before. I mean, Nathan was also just mentioned in the talk. They've become available since the past few years, and what we use in amplitude analysis, what we want to use of these frameworks is not really the machine learning part, but just the fact that they can very efficiently compute very large expression trees, so that you can, for instance, quickly evaluate some gradient descent algorithm. A few techniques that we use there are vectorization, so that you, as a Python coder, you just write some simple function, and then the framework itself does the heavy lifting of multiplying, of doing the matrix multiplications. They also come with different techniques like XLA that kind of convert your code into device agnostic code, so that you can easily distribute your processes to CPU or to GPU. And a very exciting thing, and that's what we've already seen being used in Nathan's talk, is this automatic differentiation. So if you have a certain function, most of these frameworks, they can automatically create a new function that can give you the gradient of this function with respect to certain arguments. But anyway, as a Python user, you usually only have to worry about writing a function like this. And we use this effect to insert a computer algebra system. So first of all, what is a computer algebra system? In Python, the natural choice is to use SymPy. And well, we have a small example here where we write a full small expression built up of symbols. But we should realize that what we see here, this is just some output from a Jupyter notebook, is just a rendering of what SymPy is doing in the back. SymPy represents this expression here as a tree of fundamental mathematical operations. And well, we recognize this graph already from the previous slide. And as you can imagine, this can serve now as a template to those computational backends. And in SymPy, this is called code generation or lambdification. So here we have a slightly more complicated expression tree. And then we use SymPy to, for instance, generate Fortran code. This is just a different representation of the tree you see here, or C++ code, or what we are interested in, some Jagged code here. Now, a very cool thing to realize now is that a computer algebra system can do analytic simplifications of these expression trees. I'll show you a few examples in the notebook. But if you have this easy conversion of the expression tree to this code, that also means that these analytic simplifications result in numerical optimizations in the numerical computations, right? So I mentioned CompanyBA. This is a set of libraries that we offer. The first two packages here, QRules and MForm, are encode just the kind of automated process of finding the resonances that you're looking for, as well as formulating the expression, the amplitude model as a symbolic expression. But for our purposes, the latter library, TensorWaves, is more interesting because that kind of streamlines the process of converting the symbolic expressions to those backends. It's kind of wraps around SymPy. So as I said, the first two packages, they kind of standardize amplitude analysis. That you have a single source of truth without having to worry about the computations. And then TensorWave does the conversion, and it also comes with some functionality to generate hit and miss Monte Carlo samples, and it interfaces to filters like iMinuet. Right, as I mentioned, another consequence of working with a computer algebra system is that you immediately see the expressions that you're implementing. So that's obviously quite a nice thing if you're doing some analysis. Right. I won't in this talk show you a full amplitude analysis. So here's a very short example of a very large expression. I mean, it will take a bit too much time to render that in a notebook. And what we see here is we have converted this large expression of well, more than 40,000 mathematical operations into a Jagged function, and then we evaluate it over a number of data samples. So the largest one here is 30 million, and you see that it still takes less than a minute on a single CPU to evaluate it. So that's already a nice sign that things work. What we do in the second case, we substitute analytically the certain parameters with expected values, and we do that with SymPy. We just analytically substitute them, and that has a nice effect on the performance as well. So let's now have a look at the notebook itself. Oh, just a small thing. I don't have the luxury of having two screens here, so let me quickly have a look at the questions here. I wonder this as well. So this is like, I wonder if there are other projects that have used this idea. I'm not aware of any, and this is actually one of the reasons why I showed this, just to show the idea, and maybe others are also interested in trying it out. So it's not as much as presenting this company library, it's more about presenting the idea. In fact, it would even be interesting to have a kind of a dedicated talk next year on computer algebra systems or SymPy, but okay. Let's have a look at the notebook now. I have a small cell that just hides all of the matplotlib stuff because we're not too interested in that. So first of all, in SymPy, if you formulate an expression, you have to define certain symbols, and then you apply some mathematical operations on them so that you form your expression. So we have here formulated a small Gaussian, and the nice thing in SymPy is that you can then analytically simplify, substitute things. We do some substitution here, and of course, things are done in SymPy are done very exactly. So if you would substitute this sigma with a square root, it also exactly replaces that square root with a 4 in this case. But the problem is it's not suitable for fast computations. So SymPy comes with this leptification. We have here the SymPy leptify function that takes an expression, and then you have to give it an order for the function arguments. So if we have a look at what this resulting function looks like, we see the arguments here, and we have a certain NumPy function here. So the import for the NumPy exponential function is also handled automatically here. And yeah, as I said, this is actually suitable for vectorized computation, so we can do stuff like plotting things. Right. Oh wait, let's go the other direction. Yeah. Now, TensorWaves is wrapping around this system of leptification. It does some additional. It has some additional functions like making the JIT compilation work better, and it also kind of takes care of the argument handling. So you saw just now that you have to think about where you want to place your arguments, but this is handled automatically in TensorWaves. So let's just have a look at an example here. Look at me while there's no questions. We have here, in this case, a two-dimensional expression. So we have x and y as input, and we have here the equivalent of the SymPy leptify function, but then for TensorWaves, and we create 3 different types of functions for the three backends, NumPy, TensorFlow, and Jagged. And what's important to note here is that you don't have to worry about the argument order. So this is handled by TensorWaves. It just extracts like, hey, there are 3 symbols here, or 2 symbols. So that's what we need as input. This also means that I want to go to the next slide, but yeah, there we go. This also means that the input for the function somehow needs to account for the fact that we have two-dimensional data. So we work with dictionaries where we just use the name of the symbol. Another reason to work with these strings is that in SymPy, if you convert a symbol that has backslashes and stuff, this results in problems with the function arguments. And well, in a string you don't have this problem. So indeed, if we feed this data sample to the NumPy function, you have a NumPy array as a result, and for the TF function, you have a TensorFlow tensor, and for Jagged, you get this Jagged device array. Right. So that's one of the tricks. Now, TensorWaves is intended for doing fitting, right? So we also have to have a way of taking care of symbols that are intended as parameters. So here we have again an expression that we want to be two-dimensional, taking the r and phi for like polar coordinates as arguments, and the rest of the symbols should be considered parameters that are to be optimized. So there's again like the equivalent of SymPy leptify. But in this case, we tell the function that these symbols here, the d phi, the kr, and so they are to be considered as parameters. They are carried around by that function, and they are given a certain initial value so that you can later on tweak them or optimize them. Now, imagine that you want to work with, that you measure your data in Cartesian coordinates. You want to convert those Cartesian coordinates to polar coordinates. This can also be done symbolically. So here we have symbolic expressions for the conversion to from Cartesian to polar. And tensor waves has, again, a kind of sim PyHEP equivalent where we can work with these kind of multi-dimensional expressions. So in this case, you see that we have indeed some Jagged functions that take as argument x and y and that return r and phi. Right. So this is a bit of more complicated block of code. What we see here is some wrapper classes from tensor waves that allow you to generate a block domain. In this case, with for the Cartesian coordinates. So this is just going to be a block of data. Then you want to use a hit and miss strategy or acceptance and rejection strategy to generate data sample based on those on that function that we just saw, that polar function. But the problem is, of course, that you need to convert the input data that is generated by the domain generator to the to polar coordinates. So that's why you have to give this converter here as well. And indeed, the result is again the array a data array in terms of r and phi. So let's have a quick look at what this looks like. Apologies, I have to move back. There's just a problem in this rise thing. But yeah, indeed, the distributions look nice as we expected. And yeah, as I mentioned, the function that we created is a parameterized function, so you can also play around with the arguments here. Now this is just done to create some fancy widget, but of course you want to use this to optimize your function. I'm thinking now if I could continue with a smaller example where we do a fit, or I could continue with an example where we do a fit for an amplitude analysis. Let me first have a quick look if there are any questions. From Jim, I've heard that cluster organizations suffer from expressions well. I'm not sure. We could also, if Jim wants to elaborate on this question, we could do it later on as well.
Sure thing.
But, you want to tackle this question now or continue with the
later? It's a general question.
Okay, right. So let's just. I'm thinking actually let's continue with the amplitude analysis and not so much a smaller fit example. So for this we need the two packages that are used to formulate these larger symbolic expressions. First of all, there's qrules, which, as I said, can automatically generate certain resonances that you would expect to appear between initial and final state. So in this case, we have a J psi decaying to gamma pi pi, and then we use the very nice scikit-HEP particle package to fetch quantum numbers. qrules then comes also with several conservation rules that then check which particles will be allowed in between. So in this case, we have just limited our allowed intermediate particles to these F0 resonances. And then you see the system finds 5 resonances here. This is an extremely simple example, but it's nice to illustrate to illustrate a slightly larger expression. So then we use the second library, mform, to build up an amplitude expression. As I said, it's a simpler one in this case, where we don't have these kind of interference effects from different subsystems, but still the expressions for these sub amplitudes are still relatively complicated. You have these kind of form factors, you have a whole bright Wigner, and then you have again these isospin Wigner D functions. So if you plug all of those expressions together, you have a larger expression of, in this case, about almost 1700 mathematical mathematical operations. And we can ask ourselves the question now, can we simplify a subcomponent of those expressions? We have a look at one of the nodes here. So as you can imagine, you have an expression tree where you just, in each node, you have a look at the first argument and the first one and the first one. And then we end up at this bright Wigner function here. Now you can imagine, for instance, that you want to substitute these masses of the decay products, M1 and 2, or in case you want to keep certain parameters fixed, you want to substitute them analytically beforehand. And that's what we're going to do here. So we have a certain set of parameters that, of which we guess the value. So there's a coefficient that we tweak. We have certain masses that we want to be able to tweak, and certain widths of those resonances. We can then make a distinction between the parameters that are still remaining, or the symbols that are still remaining. Those are given by the model itself. The values are also inserted from the particle package. So the particle package, of course, comes with mass values, and they come with an initial guess. So that's what we do here. We substitute the fixed parameters, and then we have a simplified expression here. So let's have a look at the effect. It's let's go back. We have here the original expression, and then the second one. It's slightly less complicated, but still, it's just to show you the idea. And you can, as you can imagine, you can make further simplifications, like you can kick out this square root, and as I mentioned, also you can make these decay product masses scalar as well. So it's just an example. Right. So again, we use this create parameterized function to make a parameterized intensity function. I'm just going a bit fast now because then we have some time to discuss things. Oh, it is again getting stuck here for a second. What? We also need to generate data, and here this conversion from the different data samples, or in this case, 4 momenta comes in handy. So we have as input, we have 4 momenta, but we want to work with those helicity angles. So this is almost like this conversion from Cartesian to polar coordinates, but then from 4 momenta to helicity angles. It's quite a larger type of expression. So it's a bit slower than I had hoped. I remember that Jim gave a talk on this rise thing and mentioned there are several disadvantages which I experience now, which is, there we go. We need to generate a data sample as well. So the previous one was just a phase-based sample so that we can do an unbind fit. And there we go. So we have generated a data sample for this function with hit and miss strategy. That will be our test sample. Normally you would take data from an experiment. Then we have given a certain parameter guess, updated that, and we see that it looks like a bit nonsensical. So what we're going to do is we use the unbind negative log likelihood method to optimize our function with regard to a data sample. And there we go. And the nice thing in TensorWaves is that you can insert callbacks, with which you can insert custom behavior into your fit process. In this case, we want to register how the parameters develop over time. So the fit result has some kind of the most useful, like the most common results that you want to have. It also passes on information from IMinuit so that you can get like the covariance matrix. And well, okay, the fit indeed worked out nicely. We have the same result. And this is the result from, let me go back again. This is the result from the callback where you register the values of the parameters over time as well as the estimator. Right. So I guess that leaves 4 minutes for some discussion. I've heard how much overlap is there between JIT compilation? Oh, and could you do this? Could you do this by itself or in the CAS? So I'm not sure if, okay, so JIT compilation is just performed over the generated code. So you have SymPy elliptification where you generate code. And in this, I showed it in the slides, right? Let me just go back to the slides here. I have been slightly dishonest here. So what SymPy actually generates is this part of the code. And what TensorWaves then does is give this additional decorator so that the code is JIT compiled. But in principle, it's just separate from SymPy or from the computer algebra system. Not sure if that answers the question though.
Right, I was asking the question, maybe a brief follow-up. So what I'm wondering is essentially if you skip the first simplification round, how much can the compilation do of the simplification that the computer algebra system would have done otherwise?
Yeah, I actually have the impression that SymPy already does a lot of simplifications. Sorry, Jagged does a lot of simplifications there. One thing that I'm sure about though is things like trigonometric functions. So this is especially important in amplitude analysis, where you compute these angles and you plug them into Wigner-D functions. So like you have to do some additional tricks here, but SymPy could simplify that. So you have like a sine of a cosine, and Jagged would, as far as I know, not be able to make that easier. This is something that we have to investigate if we can make this easier to do. But more linear simplifications, I have the impression that Jagged does do that.
Okay, thank you very much.
Yeah. Now, Jim, you had a question as well, right?
Yeah, so my question was kind of general, and I think also similar to the last one, at the base motivations of this. So I've often heard in introductions first introducing AutoDiff, they start by saying, well, you could symbolically compute derivatives, but then the size of the expressions swell, they just get bigger and bigger. But you're not finding that to be the case? Is that because of something special about partial wave analysis, or?
No, okay, now I see what you mean. So you mean because of like a product rule that you have like you already have a large expression. If you then take the derivative, it becomes even larger, right?
Right.
So this is, yeah, and this is indeed an effect that we see. So in the example that I just showed you, we do not use an analytic gradient, but I have talked with Lucas Heinrich of PyHEP, and he was like, well, this should actually not be a problem. So at the moment, there are, of course, these wrappers around the functions, and I have the impression that it has something to do with that, actually. But I mean, so to answer your question, I hear different stories. Yeah. All right. So I see no other questions, and it is past.
Yeah, I think we normally perfectly time. Fine. So thanks so much. I see that you also gave a follow-up on slides, so I suggest everybody continues there if they want to discuss further on this topic, because there's probably a lot of that you can discuss around these methods. There's more modern ways of doing things. So in the interest of time, let's then move. Thank you again very much, Remco, for this.
Thank you.
So now we have the last presentation of the first half of the session of today, and that's going to be on a different topic, namely on the modern Python bindings for the very important PyHEP 8, so the C++ PTA version. And Michael, are you around? See you around. Hello.
Yes, hi.
Yeah. Can you talk again? Seems a bit faint.
Hi, is that better?
Yeah. Maybe it's just me. I don't know. I can put it louder. There's no problem. But in any case, the sound was good. So please, when you want, when you're ready.
Okay. One moment. Yeah, I'm sorry. I'm having a little bit of trouble getting my binder to launch.
All right. We're all interactive, so there's this hiccup sometimes. No problem.
Oh.
All right, let's wait just a bit more. We're not really late anyway. We're still within time. See, Michael is still connected, so it really sounds like a technical problem with Binder. Or just the launching the book. Michael, how's that going? We can't really stop.
No, I'm sorry. Absolutely everything that I had set up broke. So I'm terribly sorry. Give me just a few minutes.
Yeah, otherwise you can also try Binder directly online if you can't do it locally on your computer. Let me check. Yeah,
No, I had a backup which I also tested, which is also not working. So
over here. What if you click on your Binder button to get it online? It takes a bit of time.
Yeah. Yeah, I was just able to launch the binder. Okay, the problem is because it's a bit of a chunky environment that the image just takes a while to pull to the different binder federation hubs. So for this particular notebook environment, it might take more than a minute.
okay, I think I've got it fixed. Okay, can you see my screen?
Yeah, perfect. All right. Cool.
Okay, I'm so sorry about that. I swear I tested all of this ahead of time. But anyway, thank you all for your patience. So yes, my name is Michael, and I'm here to present the Pythia 8 Python interface. I should say up front that I am not a Pythia expert, nor am I an author, but I was asked by the authors to present this interface, which is still relatively new, and to hopefully present it to a wider audience in case you decide to use it yourselves. If you end up having feedback for it, please contact the authors or myself, as we're all very interested. All right, with that out of the way, if you're very much encouraged to follow along with the Binder notebook, if you're able to get it to launch. So if you're not aware, Pythia is a standard tool for the generation of high energy collisions comprising a coherent set of physics models for the evolution from a hard scattering process to a multi-hadronic final state. In short, it simulates particle collisions. So the particles are produced in a vacuum. So if you want to simulate the interaction of the particles with your detector, that is not part of Pythia, but Pythia does provide interfaces to external detector simulations codes like JON4. So it contains a library of hard interactions and models for initial and final state parton showers, parton-parton interactions, beam remnants, etc. It also has a set of utilities and interfaces to external programs, as I mentioned, JON4. You can find the full documentation at this link here. So it has included a Python interface to the underlying C++ since version 8.219, but it was redesigned to handle C++ 11 with PyBind 11 since 8.301. And only at that point did the Python interface start to be widely advertised. It also allows you to generate a custom Python interface, which you can read more about here, but it's also bidirectional. So you can create a C++ Pythia object and access it in Python through your custom interface, but you can also create a Python object and pass it to Pythia, of which there's an example here. Now, I'm not going to talk about any of that in this demonstration today. The point here is to showcase the power and flexibility of the default simplified Python interface by presenting its basic features and walking through a simple event generation and analysis workflow. So it's a small standalone package and it's easily installed on your laptop. There are official installation instructions here. It's also available on CondaForge, which is the version that's present in the on Binder as well. You can also have a look at the Conda environment file here. And right. Okay, so first off, we're going to generate a single event at the LHC using the Python interface. So the first thing we do is import the module. And then we create a Pythia object. And so this is what we're going to be interacting with throughout the demo. And so you see we get this splash screen here. So now we tell Pythia what we want to simulate. And so Pythia has its own syntax, which is described in the HTML manual, which I'm not going to take the time to talk about now, but it's pretty easy to understand and just by looking at it. So for this example, we're going to simulate GG to TT bar. The process is described here if you're curious. And so we configure Pythia by passing these read string commands. So first, we're going to set a 13 TeV center of mass energy for the two beams, since we're simulating the LHC. And then we're going to switch on the GG to TT bar process. So now that we've done the configuration, we call this initialize, just telling Pythia that these are in fact the commands we want to use. And so Pythia will then give us a summary splash screen here of just the changes we've made. So we see that the process we wanted is turned on. And then let's see, if we looked at the full data output, we see also the center of mass energy has been changed to 13 TeV the way we expected. I should say that Pythia operates in GeV by default, so 13,000 GeV. All right, now we've said what we want to generate. We can actually generate it by calling pythia.next. And again, we get this splash screen. And so it summarizes the incoming beams, as well as some other aspects of the process. It then gives us the full simulated event and a summary table at the bottom, which I'm not going to walk through here, but you can look through and see absolutely everything that was created. By default, it only does this, I believe, for the first event. So if you do an event loop, you're not bothered with all this output every time. But now that we've simulated an event, we can access the event record through pythia.event. So what this is essentially a vector of particles, which Pythia expands as more particles are generated, and which you can access by index. So pythia.event braces around on the index. So the main thing to know is that the first three indices are reserved, so 0, 1, and 2. So 0 is the event as a whole, and indices 1 and 2 are the two incoming beams. And only indices 3 and on correspond to the particles that were produced in the collision as well as their daughters. And so when I say it's a vector of particles, I mean that it's a vector of members of the particle class, which store information about the particle itself, as well as information about its mother, its decay status, and so on. So let's explore some information in the event record. So as I said, we can access them by index, and recall that index 0 refers to the event as a whole. So here we just ask for its energy, which as expected, we see is 13 TeV for the whole event. We can then see the momentum of the whole event, which as expected is 0. We just had 2 incoming proton beams. Then we can check the energies of each of the incoming beams, right? So indices 1 and 2 for the 2 incoming proton beams, which as expected are 6.5 F TeV. We see their momenta as well. We can also check their identities. This corresponds to the PDG's particle numbering scheme. So 2212 refers to a proton. We get their masses, there's the proton mass, etc. You can see all the properties that are available for the particle, a member of the particle class using Python's built-in help, which will list all of the methods that are available. Let's see, you can also use autocomplete. So here we see a list of the particle properties, but the HTML documentation is the best reference. These are give you summaries, but this will really walk you through what each thing is actually doing. Now, another important aspect of the event record is that many copies of the same particle can exist in it. So what happens is, so consider the top quark that we produce in our hard interaction. Later, a shower branching occurs, right? So you have a top and it goes to a top and a gluon. So the new top, quote unquote, and the new gluon are added at the bottom of the event record, but the original top is not removed, right? So we've gone from one top to 3 different particles, right? Not 1 to 2. They're all present in the event record. But what Pythia does is that it marks it as decayed by negating its status code, which you can access with the status member of the particle class. So at any stage of the shower, there's only one current copy of the top quark. And then at the end of the shower, when the final top decays to a B and a W, that copy also receives a negative status code. Okay, so that was a lot, so let's explore this a little bit. But by implication, this here is the last top copy in the event record, right? It's ordered. And it provides the definitive top production kinematics just before the decay. So walking through this, I'll see here it's assigned top to none, and then we'll count the number of tops we encounter starting at 0. So then we can loop over the event record in the particle loop, which supports looping in Python. Then we check the particle ID of each particle in the event record. 6, again, this is the PDG particle numbering scheme, refers to a top quark. And so we assign that as the top, and then iterate the number of tops that we found in the event record. And so, so at the end of this loop, the last top in the event record will be assigned to the top name, and then print some summary information about what we did. So looping over the event record, we find that there were 13 total top quarks in the record. The final one had index 362, and it's an anti-top with ID of -6. It has 2 daughters with -24 and -5 IDs, which correspond to a B and a W, according to the PDG numbering scheme. And then we can also access its translation momentum and pseudo rapidity. All right, so as I said, particle status codes are negated when they decay. So the final state particles are the ones with positive status codes. So out of 1,330 particles in the event record, 426 of them are final state particles, which I found using implicit list comprehension here. Let's see. I have a question in the Slido, which I'll go ahead and answer. So Matthew asks if we're used to building Pythia from source, so it can point from HEP-MC2, LHAT, EDP, etc. FastJet3. Is there a way to tell the PyBind11 and bindings about them? Right, so you can customize the Python interface using basically Pythia objects. Pythia does not have sort of default interfaces to arbitrary other packages. So I don't want to talk about, I'm not sure about these packages specifically, except for FastJet. But in general, if you want to interface with our code, there needs to be an explicit interface built into Pythia. This is something the authors are aware of and would like to improve in the future. But effectively what this means is Pythia knows about JON4, so you can build an interface to it, and that's supported, but doing that arbitrarily is not really supported. That said, regarding FastJet specifically, there's also you wouldn't build your own interface from Pythia to FastJet3. However, FastJet is already built into Pythia. So for that specific case, you don't need to load any extra libraries at all. Pythia it's already in there as a class, confusingly named SlowJet. But it's called SlowJet, but it is actually FastJet, and you can read about it in the documentation. Or there's an appendix at the end of this notebook if you want to look there. Let's see. To be more, Jim asks, to be more Pythonic, would it be possible to suppress the banners and configure Pythia in an RAII way, that is, take configuration and constructor, no initialization? You do have to initialize it. So what this means is that basically, because you're passing these read string arguments and saying, configuring in Pythia how you want to generate an event, you then need to call initialize so that Pythia can parse all of the options you passed it before you would generate anything. Now, whether it is possible to take the configuration in a constructor, probably, but I don't believe that's currently supported. Suppressing the banners, yes. So basically all of these splash screens, you can tell Pythia that you don't want it to do those. There are various configurations options you can use for that. All right, so continuing on with the notebook for now, the event record only contains information about the most recently created event. So if we could generate another event, the event record is lost, right? So we've been looking through Pythia.event after we called, you recall we called above Pythia.next, which filled out the event record. So if we call that again, the event record is overwritten. So to demonstrate here, we're going to print the energy of the first collision project. So that's index 3, which we assign into the name P. We print its energy, then we call Pythia.next to simulate another event, and then we call P.E again. And so you see that the energy changed, right? And you'll notice that I didn't reassign the variable P here. It's just a pointer to the third record in the third particle in the event record. And so since the event record was overwritten, so is the underlying information that this pointer is pointing to. Now, Pythia does retain some summary information for us, though, which we can access with Pythia.stat, which gives us this nice splash screen, which you see summarizes the number of events that were simulated using the various processes. In this case, we only turned one on. It also gives a summary of their cross-section. And then, as expected, we see that there are 2 events here. So the number of tried events has to do with the underlying generation inside Pythia, different things that it attempts. Selected are the ones that actually satisfy Pythia, and then accepted, you can add user cuts. And so that's what that means. But right, we called Pythia.next twice. We see 2, that's what we expect. It'll also summarize any errors. Okay, so now let's try to expand on what we've seen so far, or to try to simulate a more realistic analysis. So summarizing the above, here's a little skeleton program. We import Pythia, create the object, configure it, call initialize, generate an event, find the top work, print some summary statistics. So then we're going to build on that to perform simple analysis. So generally, you will often want to mix multiple processes in an event. So you can simply add an additional line turning on an additional process. Here, this turns on QQ bar to TT bar. We just add this additional read string call. Now, we need to do it like this. We could not, if we called it down here, it wouldn't do anything. It needs to happen prior to initialization, or we would need to reinitialize in order for it to work. Again, we get at our summaries. So to do a realistic analysis, we're going to want to generate more than one event. So we'll introduce an event loop here. So we just move this code inside of this for loop here. We're going to simulate 5 events for now. And again, we get these splash screens. So during the run, you may end up receiving problem messages, which come in either warnings, errors, or aborts. Warnings are automatically fixed by the program. Errors mean that that Pythia has to back up and try the event again, but generally you can safely ignore it. Abort is a major problem that means that Pythia is unable to finish simulating the event, in which case Pythia.next returns false, and you ought to skip the event. So really, you only need to look for aborts in typical simulation scenarios. So what that means is that we just add these few lines to our event loop so that if Pythia.next returns false, we skip the event. All right, So again, for realistic analysis, we don't just want 5 events. So let's try doing 1,000 events. So because the event record is overwritten each time you call next, you need to find some way of preserving information between simulated events. So there are a few ways to do this. So Pythia, you can build Pythia in root or interface Pythia to root and save the entire event simulated object in a root tree. This is something that's supported by the root team, not the Pythia team, but still you can read more about it in the documentation. For the purposes of this example, we're just going to show Pythia's simple histogram class, which is nice for doing rapid checks and debugs. So this is how you book histograms. The syntax is probably familiar to you. You give it a title, give it a number of bins, low bin, high bin. And so we're going to look for the top quark transverse momentum and pseudo rapidity. And then there's, it has a fill method to which you add the numbers you wish. So the histograms support a printout function. So if we just print this, we see this output, which summarizes everything in the histogram. This is using a notation called hbook, which can be sort of tedious to look at. And if you're not familiar, explaining is beyond the scope of this presentation. But fortunately, with the Python interface, it's very simple to plot it using matplotlib. So here we simply import pyplot. We find the bin centers using the implicit list comprehension. We get the bin contents, and so this is X and Y, and then we plot them. And right, we only added one entry to the histogram, so there's just 1 point. All this cell does is turn that into a function. So if we put that all together, again, we import, create the Pythia object, configure it with our center of mass energy and our 2 processes, call initialize, declare the histograms, and define our plotting function. We then do a for loop over 1,000 events, skipping failed events, finding the top quark in each event, and then filling the histograms with its transverse momentum and pseudo rapidity. We print the statistics, and then finally we'll display the histograms. So let's see, as that runs, I believe there was one more question from Jim. For that matter, how about an array-oriented interface get events of particles as an array? Yes. Pythia does not support that right now, but I'm sure the authors would be very interested to know how many people are interested in it. All right, and our 1,000 event simulation is already completed. And here we see our transverse momentum and pseudo rapidity histograms printed out on the screen. So let's see, if we look at the full output here, scroll to the bottom. So I mentioned before that the Pythia.stat prints out this summary of errors and warning messages. So you'll notice up here, there are also errors and warnings that Pythia has printed out during the simulation. So each time a particular error or warning is encountered, it is printed, but only for the first time. If it's encountered again, Pythia doesn't bother printing it. Instead, you can see here in the summary statistics how many times a particular error was encountered. We see there was nothing fatal. We didn't encounter any aborts. And then again, here you see the number of events with the various processes we called for a total of 1,000 events with estimates of their cross sections. Let's see. So someone asks, the looping over particles in Python is going to be very slow. Is an array-based interface planned to alleviate some of the performance issues? Right. I haven't asked the author specifically if they're planning an array-based interface. And right, Pythonic for loops are pretty slow. But it depends on what you're trying to do. If what you want to do is do some quick simulation and on the cuff, I think the Python interface is actually very nice. And for that matter, I'm currently working on an analysis using Pythia that's entirely done in Python. I simulate several millions of events. And without getting into too many details, it runs, the whole analysis runs perfectly fast for my purposes and allows me to interface with the nice other PyHEP libraries in an easy way. So let's see, Pythia also can write out simple Python scripts to reproduce histograms. So we could, instead of writing our own matplotlib function to draw the histograms, we could have simply taken the Pythia histograms and asked Pythia to write out Python scripts for us, which is potentially nice. You can see a simple script for doing that here, or the documentation for it here. All right, and that is it. So we've completed a simple analysis using the Python interface. Hopefully this gives you an idea of how flexible and powerful it is and inspires you to use it in your future work. If you have feedback about the interface, you can talk to me or contact the Pythia authors. You can see it at this link here. Let's see, so we have a few minutes left. So I think we've been taking the questions as we went. So I'll continue to keep an eye on the Slido, but with the remaining minutes, perhaps we can walk through some of these appendices. But perhaps I should consult the chat. No, this is not relevant. Okay. So the first appendix here is input files. So Pythia supports these command files, where instead of calling those read string functions at the top of our file, we could instead simply have these command files, which Pythia can read in and set all of these settings at once, which makes it very easy to discretize your Pythia runs. So for example, in my analysis right now, I use several different Pythia configurations. And so I simply have different command files, and then I read in each one and run the same Python generation scripts and analysis scripts with just different command file inputs, which is very nice. You can walk, the appendix goes through this in some more detail. Let's see, you can also find a fuller description of the event record in the appendix, which describes more about the various particle ID codes and other things that are available in it. It gives a nice introduction into the sort of things you can access in there. I recommend it. There's more information about histogramming down here. And then there was a question about FastJet. And so you can see this jet finding appendix, which again is confusingly named SlowJet. Formerly, this made more sense in the past. This is basically a legacy name. These days, it really is just FastJet. And it's distributed inside Pythia, as I mentioned before. You see here an example of how to set it up. With this call to SlowJet, you set these options for the algorithm, etc. And you can simply set it up with this, and then you can analyze an event by passing the Pythia event directly to it. Okay, and I think that's it. Any other questions?
Yeah, I guess I'll just ask mine verbally instead of trying to type it into the chat real quick, although I can also do that. So thanks for the talk. So this is maybe more of a meta question about Pythia as well, although you know that you aren't an author, so I appreciate that we should maybe just ask them. But so Pythia has a GitLab repository where there are releases, but is the source code for Pythia publicly available in a way that people can contribute to, or is Pythia itself basically a project that exists in a private area that then only has public releases?
Yeah, that's a good question. So the Pythia release model, I believe, oh boy, I believe focuses mostly on, is mostly handled by the authors. The code you can access. So when you download Pythia, you don't just download a binary, you download the whole source code. And so the whole thing is available that you can interact with and ask questions for. I don't believe, my impression is that they don't necessarily invite pull requests in the way that open source repositories do. I think they mostly want you to contact them directly if you have contributions or things you'd like to see added, but take all of that with a grain of salt. As I said, I don't maintain this package.
Okay, yeah, thanks. That was kind of my assumption, but your input was helpful there.
But right, of course, if you want to contribute, you should contact the authors. I think they'd be very happy to hear.
Can I comment on this? Do we have time?
Sure.
So yeah, I mean, I just talked about the very same issue recently to one of the PHP developers, and it's just there's some people in that group who are very conservative, and that's why they don't. I mean, they internally have a GitLab repository, but so far they didn't make it public, and it's in discussion. So maybe this will happen at some point.
Thanks, Hans-Peter.
Okay. Let's see how that materializes. All right. Thanks so much, Michael. I have to say, and I think just summarizing of some of the comments that were given, I think one of the common theme is that not everything is very Pythonic. So if the authors, maybe that's a general feedback. If the authors want to make a little bit more Pythonic to have the common theme with the rest of the ecosystem, I think that would be nice. Certainly, I'm biased, but certainly I would I'll make that statement.
So no, right, and I will certainly pass that feedback along, especially the comment on vectorization. So having used some other Python interfaces to underlying C++, and just in terms of usability, I find it is already very easy to use. So, right, you have to, this kind of configuration and initialization process is not particularly Pythonic, but it has sort of enough Pythonizations that I find it's already fairly intuitive by comparison, especially to some other packages. But yes, I will certainly pass.
It is nice. It is really nice. That's why we're taking it. But okay, but we can always continue in slides while we're here. So in the interest of time, just to get everybody a proper break, especially that today we have the hacker shop later on. Let's then reconvene in half an hour at 4:30. So have a little break and see you later. Thank you.
Okay, so it is 30 minutes past the hour, so we can conclude our break now, and we can get started with the second half of today's session. And to kick us off, we're going to have a tutorial session on end-to-end physics analysis with open data, focusing on the IRIS-HEP Analysis Grand Challenge. And this is going to be presented to us by Alex Held. Alex, if you're ready, you can go ahead and take it away.
Excellent, Matthew. Right, yes, I'll get my screen sharing set up. And indeed, as you were saying, this is going to be a description of what we're doing under this name of Analysis Grand Challenge. And to get us started here, I'm going to have a few slides just to set a bit the scene, and then we're going to jump into a notebook and going to go through that and see things actually happening in practice. So a few things I need to explain at the beginning here. There's two words here, IRIS-HEP and Analysis Grand Challenge. So what IRIS-HEP is, it's a US software institute for research and innovation in software and high energy physics. So this is paid by the NSF. And what we're doing as part of this institute is we're doing research towards the high luminosity LHC. Why are we doing this? Because we're going to be taking a lot more data at the high luminosity LHC in the future. And the data processing methods that we're using for physics analysis don't scale so well if we don't get substantially more resources allocated in the future, which we don't expect. So we need to improve our methods so that we can still do all the interesting physics that we plan to do when we have much more data in the future. So that is what this IRIS-HEP Institute is doing, and there's different areas that tackle different aspects of that. Now, since there's a lot of different pieces that come together when you want to do a physics analysis, you not only need software to do that analysis, you also need resources on which you can run this analysis. And in fact, IRIS-HEP is working on quite a few of these different aspects in its attempt to provide sustainable analysis pipelines. One thing that we need then is when we have all of these different efforts to bring them all together. And this is what we're doing under this name of Analysis Grand Challenge. So it starts out as an integration exercise really for IRIS-HEP, where we take all the pieces we're working on and we're putting them together, we're putting them to the test, where we have a physics analysis that is realistic in scope and scale. And we test everything that's being developed, all the things available in the ecosystem, can we put them together and do they satisfy the requirements that we have? So it starts out as that. It starts out as an integration exercise that's bringing together all the different pieces here, where we can deploy the software we're developing on analysis facilities, and we can demonstrate, yes, we can do physics analysis with that kind of setup in an efficient way. But then it goes beyond just this integration exercise, as I'm going to try and highlight in a second here. Now, I've said the word analysis a few times, so let me clarify a bit what exactly we mean by that, because depending on your background, you might understand different things under this word. So in view of the high luminosity LHC analysis here in the context of what you do as a physicist doing a physics analysis, starts at some point from a common set of data samples that are going to be centrally produced and available to you. And then starting from that, all the subsequent steps that you need to do in order to go from that data to the results that you can publish in your paper is what we understand under this term analysis here in this context. So you're going to have to extract all the relevant data from these files that are going to be provided centrally. You're going to have various types of objects in there that you might need to calibrate or recalibrate, and you might need to evaluate different calibrations for the purpose of evaluating systematic variations that you need to consider. Then you probably aren't interested in all the events that are going to be available, so you're going to have to filter out those that you care about. And you also might want to calculate different types of observables that you're then using in your analysis to increase your efficiency. You may want to build histograms. If you want to do a binned analysis, you don't have to. But here in this case, we're going to be looking at the case where we do have histograms and do a binned analysis. And then from those, you want to build a statistical model that you can then use to perform inference and get the results that you ultimately can publish. In order to do so, you're also going to have to visualize all of these pieces to convince yourself that what you're doing is indeed the right thing that you intend to do. So there's various visualizations along the way that are crucial to be able to look at so that you can develop your analysis and that you can disseminate the results. And then you don't just want to do this once. During optimization of this analysis, you're going to do this many times to various extents in order to optimize your analysis. And then ultimately also you want to preserve your analysis so that it can still be reproduced, that you can rerun parts of it, that you can use it, for example, with a different type of signal in the future. Again, rerun a piece of it and get a new result out of that without having to put lots of additional efforts into it. So that is another aspect here of what we're looking into. Now, what is the task that we're trying to tackle under this name of Analysis Grand Challenge? This is what I'm describing here briefly. So it's about something that is quite common at the LHC, namely top quark pairs that are being produced, and we're doing something that is fairly simple in that context. Where from a high level point of view, then once you go into the physics details, it gets complicated, but we're measuring the cross-section of top quark pair production in a specific final state. That includes a few pieces that we're going to be looking at in a second in the notebook, where we're constructing a top. You can see a plot as a spoiler for the notebook on the right here. And it's a fairly simple setup, but it's one that is quite flexible and can easily be extended to capture various other types of use cases that you might have in practice at the LHC. And one thing that we're focusing on specifically here in this setup compared to other types of example analyses is that we want to demonstrate also the handling of systematic uncertainties, as those are something that people in practice need to deal with, and that can be a complicated thing to handle. So we want to focus on getting a nice workflow that handles those well. We are using open data from the CMS experiment. And it's important to us that we do so because by us using open data, it means that you can actually run this analysis with us. You can go on and use the notebooks that we're providing here and do your own analysis with that. All of that data is publicly accessible and available to everyone. And in total for this year, we have about 4 terabytes of n-tuples available. We're not processing all of them today. I have to tell you, unfortunately, Binder isn't going to give us that much compute for every single participant, but you are processing a piece of that data set if you're running along on Binder. And I want to stress that the setup that we have here is not meant to discover any types of new physics or make a really detailed physics measurement. What we're looking at here is demonstrating a workflow and demonstrating functionality, but all the physics details are not going to be correct. Because we're focusing on that functionality. And if you really want to extract physics from that, you're going to have to work more on implementing all of the systematic variations, for example, in the correct way physics-wise, but that is not the focus of what we're doing here. So this demonstration is about functionality. What I have on this slide here in this figure on the bottom right are the points that analyzers typically suffer from when they do a physics analysis. And the number one point here is the handling of systematic uncertainties. We'll see in a second how we do that in our kind of setup. But because those points here are those that analyzers name when you ask them, okay, what is difficult to do? Because of that, we're focusing also on a setup where we do hit and touch on all of those points so that we can test, okay, how is the workflow in our kind of setup and how painful are these different points? So that we can evaluate then also what can we improve so that the user experience in the future is going to be better. There's going to be a lot of different libraries, services used in our demonstration. You can find some logos here. We'll see more in the notebook in a second. Those are also all links. If you want to look at any of the libraries here in particular, just click on there and you will be brought to more information. So this is just to say we're really trying to bring together a vast offering that's available here in this ecosystem in order to do a physics analysis with all the pieces required. Now today, you're going to be able to run on Binder, but in practice, if you're trying to process large-scale physics data sets, that's not going to be sufficient, and you're going to have dedicated resources available to you. And one thing that we're also investigating and developing in the context of IRIS-HEP is this prototype analysis facility under the name Coffee Casa. I'm going to be running the demonstration from there today myself. It's going to be the exact same notebook that you're also using, but this is something that we're developing and using to test how we can perform physics analysis that we then can also scale to additional resources so that given that we have these resources available on these dedicated facilities, we can actually perform analysis efficiently and in a sufficiently fast way for fast turnaround time so that people can quickly get to their physics results that they care about. So lastly, here on this slide, next steps and plans for the future. This project is ongoing, and there's various directions in which we want to expand. So the analysis that I'm going to present, we would like to expand in a few ways, most notably adding a machine learning component. We have different implementations of the analysis task available. You will find them also linked in the notebook, and we're curious to compare them in order to see how the usability and the performance of the various different approaches looks like. Next, we're moving on to benchmarking to study at scale how the performance is. And in the longer term, what we also have as a stretch goal is related to what Nathan was just showing in the earlier session. We would like this pipeline or part of the pipeline at least to become differentiable so you can automatically optimize your physics analysis as well. If you would like to stay in touch, please join us on this mailing list down here where you can sign up. And I'm presenting this project today here, and the project is co-coordinated by Oksana, who's also connected, and me. But there's a lot of different people and a lot of different projects behind all of this that make it happen, because there's so many different libraries here and services that we're using. So thank you very much to everyone who has contributed in one way or another. There's a large group of people behind all of the different projects. All right, and then with this, we're going to transition over to the notebook. And the notebook now is going to bring us throughout a physics analysis, all the way from reading our input data to getting some results through statistical inference. You're welcome to follow along on Binder. And I'm going to have a Slido open in parallel. And since we're going to be hitting on many different pieces here, please feel free to put questions on Slido anytime. I'll try to address them as they come up, because we're going to be moving through different pieces, and it might be easiest to sort of address the question right when we're talking about the respective piece. I'll also try to open the Zoom chat, and I see a first question. The mailing list is open to anyone. Yes, the sign up link there is open to anyone. You're very welcome to sign up to that list to follow the developments. All right, and then with this, click the link on Indico if you want to follow along the notebook yourself. And I'm running on Coffee Casa, as you can see up here in the URL. So up here is just a bit of an introduction of what I just already told you about. And then the first image here in this notebook is, again, the kind of pipeline that we're looking at. And what's also here now are all the different logos of the different libraries we're using here. So just to give you the overall large-scale plan of how we're going through this. We're going to have some columnar data. That is our input. We're going to read that data, filter out the events that we care about, evaluate systematic uncertainties, construct observables we want to use, and then fill them into histograms. We take those histograms to build a statistical model, which we then serialize in a so-called workspace. And then once we have that model available that we then saved in this workspace, we perform statistical inference, get out results, and visualize them, and then we can go on from there. We're going to go through this pipeline in two different ways, but then you will see that we're going through them in two different ways that have different advantages associated to them. There are links here to other talks because we're going to be touching, like I said, on lots of other projects. So please check them out for more details on the various pieces that we're using today. Okay, that is enough preamble. We're going to start out by setting up all of our inputs, all the libraries we're using. And the very first thing you're going to see up here, the very first piece of content, is this thing we call AGC schema. So AGC stands for Analysis Grand Challenge. So this is the project that we have here. And what this schema is doing is that it will group all of the columnar data that we have together in order to make it really convenient for us to access. And since that might sound a bit abstract and this might be a bit hard to read, instead of going through that in detail, let me just show you what this schema does exactly. And we're going to do so by exploring a single file of data that is in our data set. It's typically a good idea to start out by exploring something quite small, because then with this, we have a fast iteration time. So if you start executing the cell here, you're going to download a 200 megabyte file, just as a warning if you're on a limited data connection. We have it already, so here in this case, this runs quite quickly. And then what we can do here is we can open this file with just read it with uproot. And if I uncomment this line here to look what's inside that file, then we're going to get the list of all the branches inside that file. And you see, okay, there's quite a lot of branches in here, quite a lot of information. And now you can go on from here and you can use Awkward, for example, to start analyzing your data from here, no problem. However, we're going to be using Coffee in this demonstration here. And what Coffee gives us is this possibility to specify this schema that we just looked at in the cell above. So let's do that and let's see what we get out in this thing that is called events, which is what we get from this nano events factory reading that same root file that I just opened manually with uproot. And now suddenly we just get a few types of fields out of that correspond to different physics objects. And we have grouped essentially all of the columns that we care about into these objects. And now we can reason about the data that we have in terms of these objects. So it's much more convenient to now use those because everything belonging to jets, for example, is grouped together under this jet name. And we also have behaviors associated to this so that we can add jets together. And then in the background, automatically the addition of these 4 vectors is done for us. So we don't need to think about it. It just works automatically in the background through what Coffee provides here through this schema. You can also accomplish this with Awkward directly if you want. So just to demonstrate here, we can now access, for example, the jets in the event, and then we can access .pt. And now what we get out of that is the PTs of all our events. You can see there's about 42,000 events in that file that we're reading. And then there's a variable dimension here because in each event, we're going to have a different number of jets. And then this is the PT then per jet that we have. All right, so now let's just have a brief look at our data. Let's just see what's in there. So what this line does here is it counts the number of jets, which is what this here is, per event and puts that into a histogram, which we're going to construct with hist. And then we get this nice visualization here. And we can look at it and see, okay, there's actually quite a lot of jets. So this peaks somewhere around 10 jets or so. And you'll see in a second how TT-bar this topology looks like if you haven't seen it before. But I can tell you already right now, that's quite a lot of jets. So that might be a bit surprising. However, what we can do is we can filter out all of the jets that have really low transverse momentum, which we're typically not going to care about much. And we're going to do that here and plot the same thing again, this time calling here .plot and then plotting through matplotlib. You can see the same distribution here where we have now plotted again the number of jets. After this requirement of each jet should have 25 GeV in PT. And now we're peaking somewhere around 5 or 6 jets, which is more reasonable, what you would expect when processing this type of data. Okay, let's now do one more thing with this data and to show you a bit more of the columnar processing we can do, which we're then also going to stick into Coffee. So what we have here is the production of top quark pairs. We have incoming proton beams, they collide, they produce a top quark pair, which are the 2 red bubbles here, if you want, and those decay into bottom quarks and W bosons. And then everything that's surrounded here by a black circle is what we can observe, or rather the remnants of that ultimately what we can observe in our detector. So some of the things here we cannot observe, like this neutrino down here. But in this type of topology we're looking at, we're going to expect 2 of these B quarks. We're going to expect 2 additional quarks here. All of those are going to create jets in our detector and 1 charged lepton down here. So this is everything that we expect. And now what we would like to do is reconstruct the mass of one of these tops. And there's one way of doing that, which is by identifying that the transverse momentum of these top quarks is going to be balanced, assuming that there's nothing else happening in the event. And then we can just pick the pair of 3 different jets that maximizes the transverse momentum when you sum them together. So in this case here, that's typically going to be these 3 jets up here. One of them is going to be B-tagged, and then there's 2 additional ones. And if we sum all of them together, we're going to get something that resembles the top. Now, this is a statement that I made, but let me prove to you that this actually works. And this is down here in this cell, which is sort of like the algorithm that we're going to use. Again, just using Awkward, we're going to look at our events and the electrons, muons, and jets, and select all of those that have transverse momenta above 25 GeV. Then we're going to look at events that have exactly 1 lepton, which is what the line down here does, at least 4 different jets, which we expect from the event, and one of them should be B-tagged, which is down here, because, sorry, at least 2 of them should be B-tagged because we have 2 B quarks in our event. We apply all the filters, and then here, down here is a bit of awkward magic to make things happen. So we're looking at the combination of 3 jets that maximize the transverse momentum. So let's just calculate all of the possible combinations via awkward down here, get the floor momentum of the of this 3-jet system for all of the different combinations. Make sure that there is at least 1 B-tag jet down there, which is down here. We're checking that the maximum B-tag from all the 3 jets is above threshold. And then we take the system that maximizes the PT, which is what this is, what's down here, and calculate the mass. So that's a lot. Feel free to take a look at it again afterwards to convince yourself that we're doing the right thing here. Ultimately, we fill everything into this variable, and let's plot it and see what comes out of it. This is the distribution compared to where you expect the top mass to be, somewhere around 175 GeV down here. It looks pretty good. So we have nowhere used this assumption that about the top mass being at this value, but still we're peaking around this value. So the algorithm seems to be working. Okay, so now we have a simple kind of setup, a simple algorithm that we might use to build some kind of observable and to construct a histogram that we might want to use in our analysis. Now let's start scaling things up. And the way that we're going to do this is by using coffee. There's a bit of configuration now up here where you can specify how many files you exactly want to run over, up to 3.5 terabytes, but I don't recommend doing this on Binder because you probably will run out of memory and it will probably take way too long and your Binder instance will not make it. So I would suggest leaving it at all the default values if you are running and following along on Binder. Here's the data pipeline that we're now looking at next. We have our input data, which is shown here in green, and then we're going to use coffee. And what the different bands here are representing is coffee processing a chunk of our data. The time runs here from left to right, and we're going to be able to parallelize the processing of all of these different chunks in this MapReduce pattern here that we're using. We're doing the same types of operations on all of our chunks of data, and we're writing out histograms, which we then in the end aggregate, we sum them all together and get out a single histogram ultimately. In fact, we're going to get out many different histograms, but we're going to sum all of them together. There's a bit of global configuration up here. We're just going to go through that. We don't need to change anything there. We're going to come back to this a bit later. So what we need next then is a processor that we can use to do this type of data processing. The processor is defined down here. Let's look at that first, and we are going to come back up to these variations up here. We're going to have a histogram. This is a multidimensional histogram, and this is where we aggregate all of our data. So what do we have in this histogram? We have one axis, which is going to capture the observable that we're trying to build here. We are going to have another axis, a categorical one, which is going to correspond to 2 different regions of phase space that you will see in a second. We have a selection where we request 4 jets and exactly 1 B-tag, and 4 jets and 2 or more B-tags. 2 different phase space region on this axis. We're going to have another categorical axis that corresponds to the type of physics process that we're filling in, and yet another one to the systematic variations. We need to consider systematic variations here because there's uncertainties related to many different things, and we want to capture them so that we can propagate them and ultimately correctly use them in our statistical inference so that we get a result that's not unrealistically optimistic just because we forgot to take into account some uncertainties that do exist. We can take advantage of metadata that you will see in a second coming back to read out information about the data that we're processing. And that can be very useful when you're using coffee here because you might want to specify additional information about all of the different files that you're processing. We're going to normalize all of our events to the luminosity from 2015 that CMS recorded, which is what we're using here. And then what's happening down here again is what we just looked at above, just doing it standalone and awkward. We just took that code and we put it into our processor. We do the same type of selection, selecting events that have 4 jets, at least 1 B-tag here, and a PT requirement on all the different objects. And then we're looping over the two different phase space regions that we're looking at here. In the region with two jets, we have the same type of algorithm that calculates this reconstructed top mass. And we have yet another region of phase space that we're also using here, where we have a different observable, the scalar sum of jet PT that we're filling in there instead. And then at the end of the processor, what's happening is this histogram object that we have that has all of these different dimensions here. We're just filling that, and we're filling that for all the different systematic variations, but we have all the histograms that we might want to need in here. So let me go back to these systematic uncertainties because they're coming up here. We defined a few functions up here for various types of systematic uncertainties. So let's look at this one, for example, which is the jet transverse momentum resolution here. What it takes is the transverse momentum of a jet. And then what we have here is essentially, we're calling a random number that smears our jet PT around a bit to kind of simulate that we might be overestimating how good our resolution is. So we're smearing things out a bit here. Now, in practice, if you're doing this in CMS, the function is going to be looking a bit more complicated. And ultimately, what you would do, for example, is you would call correction lib as Nick has presented. But what we care about here is just showing the workflow. So instead, the demonstration here just uses a simple function that captures the essence of what we're trying to do. We're going to call a function that gives us back a new variate jet transverse momentum. Now, if you do something like this that changes your transverse momentum of a jet, then that has implications. So we need to, for every systematic uncertainty, we need to do the exact same analysis pipeline here. We need to do the same type of calculation, but the calculation will be different depending on the properties of our objects. So if the jet PT changes, for example, since we have down here a requirement where we say we select jets that should have a PT above 25 GeV, now this needs to take into account that this is going to vary as a systematic uncertainty if you do apply this calculation up here. And that's why we fill it here in an additional, into additional property of this event, which is up here where we say, okay, actually the PT is going to vary, and we take that into account and we propagate that through our processor. So there's different types of uncertainties that we have up here, some which only change the weights of the different events and some which change the properties of objects. And I think I will leave it at that level of detail right now. I'm happy to go more into this if there's questions, but this is something that you will have to deal with when you do this in practice. And this can make your logic of the implementation of your physics analysis code significantly more complex depending on how you approach this. So for now, let's accept that cell. So we have a processor available now. What do we need next? Okay, we have something that does our calculation, but we need to construct the actual input. And you will see here that we are calling out in the cell to a utilities file that contains a bit of code just to not fill up this notebook too much. And then effectively what we're getting here is a dictionary that looks like this excerpt down here. So this dictionary is going to have different keys, which are up here, which are different physics processes, production of top quark pairs, and then various different ways of doing this production corresponding to systematic uncertainties, ultimately production of single top and production of W plus jets as well. The different physics processes here are going to be associated to a list of files, and those files up here are publicly accessible. You can use them yourself, and there's metadata that we associate to it as well, such as the cross-section for a specific process, which we're then going to be able to access in the processor in order to make use of it. Okay, so we have a processor that does the data processing. We have constructed the input in this big dictionary here that we want to process. So it's time to actually execute everything. And that's here in this next cell. I'm going to hit start, and you can see there's a progress bar happening. There's two steps happening here. The first is the pre-processing stage in Coffee, where we just look at our files. Essentially, we check how many events are in there, and then Coffee splits it out into chunks of work. The second step that just finished is the processing stage, where we then actually call the processor code to do the execution. You see, this finished very quickly. And the reason this finished so quickly is because we're only processing a small number of files in here. This is only about 2 gigabytes. We'll scale it up in a second. But if you're running along on Binder, this might take a bit longer because you're going to stream these 2 GB essentially to your Binder instance. So this might be slightly slower. So what we got back then from running Coffee is this object here that I called all histograms. So let's see what's in there. So if we just add it down here in another cell, you see this is a histogram with all the different axes here. And because we're going to have a high dimensional object here, maybe let's do some plots in order to have a better idea of what's in this histogram and to convince ourselves that we produce something sensible. All right, so the first plot that we have down here is now the plot of this phase space region where we select at least 4 jets, and one of them should be V-tagged. And let's see the types of processes that contribute here. So we have TT bar, top quark pair production, contributing here in this yellow color, as would be expected. And then there's a big contribution here in purple from production of W plus jets, which also makes sense because we only require a single V-tag. So if you're working in this kind of topology of phase space, if you're looking at this plot, this looks like a sensible outcome. So everything here seems to have worked. Let's also look at this other region of phase space that we already took a look at when only processing our single file up top, which is this region where we have now a requirement of 2 V-tags. And this is now where the top quark pair production really dominates. So almost everything in here is yellow. We see again a nice peak around the top quark mass. So still things seem to be working. The difference to the simple example above is that above we just processed a single file. Now we've processed all these different processes as well, not only the nominal distribution, which we're looking at here, but also different systematic variations. So let's take a look at that, because so far you haven't seen the systematic variations. So let me convince you that we actually did process them. And we're looking at them down here. What's cool here is that we using features like this specifically is what HIST gives us through this universal histogram indexing. We can rebin the histograms just on the fly, merging bins together. We can just do it like this. And we're looking here now, we're slicing at this region of phase space with 1 V-tag requirement at the process of TT bar and at different systematic variations. We're plotting all of them. And you can see here now that there's different distributions. So indeed, our predicted template for the different TT bar distributions here under the systematic variations changes a bit. So this systematic variation does have an effect on our results. So we better take it into account when we move on to the statistical inference. We've not only done V-tagging variations, we've done other ones. We have some jet energy variations, for example, that we're looking at down here. You can see those look a bit more similar to each other. There's a small effect here only, but you can also see there's different histograms that were all filled, and they slightly differ from each other. Okay, so we have everything in this high dimensional histogram. Let's make sure we're not losing it. So let's save it to disk. There's a utilities function. Feel free to take a look at it. It's in this folder called utils, which if we move into it, is down here. It's this function up here. If you're interested in taking a look, it's not really doing anything interesting. It's just going through that file and saving everything to a histogram in that root file. So we have that all now saved. We have all of our histograms saved, which means it's time to move on, build actually a statistical model from that, and perform some inference. What we're using here then to accomplish this task is this library called cabinetry. And the very first thing you see down here is that we're loading a configuration file. So we probably better have a look at what's inside that configuration file. And let's do so. This configuration file now specifies in sort of like from a high level viewpoint and from kind of a physics viewpoint, what the statistical model that you're building should contain. So there's a few settings up here. We're not going to go through everything in detail. There's not enough time for this, but you're welcome to check out the previous talk on cabinetry at the last PyHEP that is linked at the top of the notebook. So we have a few physics concepts here. We have different regions of phase space because we filled 2 different regions of phase space. So we specify them here. And we also specify a path because ultimately all of our histograms are going to be looked up in this path that is up here that has a few placeholders, and everything that's a placeholder like this region path thing here is going to be filled in by the options that are specified down here. Then there's different samples available. We process TT bar, W plus jets, and so on. There's also this thing here called pseudodata. We're not actually fitting real data that CMS took. We're building our own pseudodata version of that. Reason for this is mostly to avoid any kinds of issues with the data being in bad agreement, because we're cutting some corners here. So we're just building a pseudo data set ourselves that is in reasonable agreement with data, but there's nothing with the Monte Carlo prediction, but there's nothing fundamental about this that prevents you from using actual data here. So we enlist all of the different samples. And then lastly, we enlist all of the systematic variations again, and we have some configuration options for each of the systematic variations that tells you how it's built. And it's referring back then to all of the different histograms that we have just filled into our histogram root file. And lastly, there's normalization factors. So we have one normalization factor here, which we call TT bar underlying norm, that acts on TT bar. And that is the thing we want to measure. We're going to measure the normalization of this TT bar process, which then is proportional to this TT bar cross section. Okay, so that is how the configuration here looks like that we just loaded. Let's move back into the to the talk. And what we're going to tell Cabinetry is then, okay, look at this configuration, collect all of the template histograms that are specified in there, and build a workspace. And then for completeness, we're also going to save that workspace to a file. You don't need to save it, but just let's keep it around. Let's save it to a file, which we did here. We can take a look at it. And what we have down here now is a PyHEP workspace. The visualization of JSON files here on in this case is a bit difficult to see maybe, but if you download that JSON file and you view it in another editor, you can see now the structure of this workspace, which contains the statistical model that we're going to be working with in this JSON format specified by and used by PyHEP. We can use now PyHEP to go ahead and do inference with that. And we can use also command line utilities here to take a look at that workspace. PyHEP provides this, and here's a summary of what's in there. 2 different channels, the 2 different phase space regions, 5 samples, 40 different parameters. We have 11 bins per channel, and these are the samples down here. So PyHEP understands what this workspace is, because otherwise it would have complained here that it doesn't know how to pass that file. So everything seems good so far. Okay, so then let's actually take that workspace and let's perform a fit of the statistical model that we have here to data. That's what we're doing here. What we're doing is we're using Cabinetry to perform a maximum likelihood fit. Cabinetry calls PyHEP to do that, and PyHEP actually calls IMinui internally from how we have configured it to perform this likelihood maximization, or rather negative log likelihood minimization. So we're getting out of that the status report here, everything is good, which is good to see. The uncertainties and best fit values for all the different parameters. And we can also visualize the results of this fit. Down here are the results for all the different nuisance parameters with how pooled and constrained they are. If you are now a physicist, you might get very worried about how constrained these 2 parameters are down here. That is essentially because they have very large effects. They shift the prediction by quite a lot. And we have an incomplete model here. In practice, you're going to add additional nuisance parameters, which will relax all of this a bit. So don't overinterpret this in terms of physics. Again, this is just a demonstration of the workflow here. You can get all of the usual things you might want to look at back from this. So we can look at the correlation matrix, for example. Here you'll see the correlations between all of the different parameters. We can look at, okay, what was actually the best fit result for the parameter we wanted to measure, this normalization for TT bar. You can see the best fit value is very close to 1. So it's an agreement with our prediction, or if you want, it's an agreement with the standard model with an uncertainty of about 6% here. And if you've done this fit, you probably also want to see, okay, how are the distributions looking that we actually fitted? You can see the distributions before the fit is performed alongside uncertainties here with all the statistical and systematic uncertainties. You can see the uncertainty band is quite large before the fit is performed. We have them in both the regions of phase space that we fit here. And we can also calculate the post-fit version of this plot where we now project the fit results onto this. You can see we have significantly constrained in this profile likelihood fit all of these uncertainties, the uncertainty band, to the statistical power that we have from data. And everything is in very good agreement here. The model fits our data very well. Okay, so I'm going to show you one more thing down here, which is some upcoming features in Cabinetry, because we're actually using a version that isn't even released yet here. just to give you a bit of another look at this statistical model that we just built. And what this function here does is it visualizes the structure of this model. So the structure of this model here in this kind of visualization looks at the different phase space regions that we're fitting, 2 of them. This region with 1 BTEC, this region with 2 BTECs. There's different samples available, the different physics processes that we have. And then there's different parameters available. Those are the parameters that were used in our fit. And then what the different colors here tell you is what types of modifiers are acting when you change a different parameter, what happens. So if like something here is green, for example, that means this parameter controls 2 different modifiers on a specific sample in a given phase space region. So this, if you are familiar with PyHEP, tells you a bit of how the model looks like in terms of its structure. You can visualize this in different ways. This way, because inherently the information is sort of 3-dimensional, there's 3 axes here, and we can't easily visualize 3 dimensions, so we split the 3rd dimension essentially into 2 different plots. And there's 2 different ways to plot this. You can, instead of splitting it by phase space region, you can split it by sample and do the same type of plot. And depending on what you might be interested in, one or the other of the visualizations might be more useful. You'll also get you can also get tables out of this with uncertainties. You can actually save them as LaTeX or as any other format, as Markdown, as HTML, as anything you really want via this tabulate library that is being used here. Here's just an example of the yield uncertainties for all the different samples and the total model prediction after the fit has been performed. Okay, so now we essentially have the pieces that we can put in our paper. We can put this kind of table in our paper. We would probably want to put these type of plots in our paper. We have the results for the parameters that we fitted. So we're good in some sense. Now, one thing is we only processed a small amount of data. So let's try processing a slightly larger amount of data. Before I move to that, let me check Slido and Slack to make sure I'm not missing anything important. Okay, looks like not so far, but feel free to ask something if things come up. So let me move ahead and show you what happens if we process a bit more data than before. So on Binder, you have this value up here set to 50, set to 1. I'm going to set it to 50 now. And we're also going to use task. On Binder, that's false by default. We're running somewhere here where we can actually scale out a bit and use more resources at the same time. So I'm changing the settings up here, and I'm going to run through these steps again. And I'm again doing the step here, executing the data delivery pipeline. Now I'm moving over to Dask here, and what you see now here is the stream of tasks that Dask is processing, and it's already moving quite rapidly because everything in yellow, that was the pre-processing where we just look at all of the different files, and we take a look, we see how many events are in those files, so that we can then split it up into chunks of work that need to be executed. And those are then being executed. That's everything that's here in blue. You see we're already halfway done with that as well. So here, now what is happening is Dask is going to run jobs that process all of the different chunks of data. And this is happening here in parallel on multiple different threads. And then once this is done, every piece of work here is going to produce this 5-dimensional histogram. In the end, everything gets accumulated back, merged back into this one master output, and we just get these the same type of histograms back that we had before. So this object is going to look the same, with the only difference that we process more events now. So our statistical uncertainties are essentially going to be smaller. But we can run, again, the same steps that we have run before, and we're going to get the same types of plots out of it. We did the same thing, we just have more data available. So I'm going to go back through the same stages that we just had, which are all going to give us the same outcome. Now, in practice, you want to scale here to many hundred cores at the same time, ideally, so that you can really have an interactive type of workflow where your analysis runs so quickly that you ideally can spend your time then looking at the results, studying the results, making conclusions of what to do next, and you're not being blocked by things that take a while where you're waiting on them. Now, if you are running on Binder, there's one thing, I saw in the chat, it was actually quite fast, apparently, but there's one thing that might be making things really slow if you're running with a larger number of files. And that is the problem that we're currently streaming all of the data that is being processed to Binder, or in this case here, to this notebook that I'm running at this Coffee Casa instance. And in order to address this issue, we're going to look now at a different data processing pipeline. And this is where Service X comes into play. So if you were following yesterday, you will have seen Kyungyeon's talk where he already presented Service X. So let's take a look at how we're making use of it in this setup. The first pattern up here is what I've shown you already. We have our data. Our data is accessed by all of these different coffee processors running in parallel, processing chunks of that data. We aggregate everything back and we output this big histogram. But the data being streamed here is all of the data, potentially all of the columns we might want to access. And it also doesn't really include any kind of pre-selection. So if we know, for example, we're going to only care about events that have lots of jets in them, we could, in principle, reduce the amount of data that needs to be transferred at this step if we already selected only those kinds of events that fulfill the requirements that we might want to make. In practice, at this stage of physics analyses, your jobs are often going to be limited by the input and output, so just by the transfer of data. And if this is a limiting factor, then you really want to reduce the amount of data that needs to be transferred. And one way in which you can do this is you can have another step running at first, which reduces your data already, so that you're then only sending further additional data that's really needed for subsequent processing. And if we use Service X here, what will happen is that we're going to have another step at first, where we set up a query that specifies, okay, this is the data we really need. This data is then going to be processed by Service X in parallel at sites running ideally very close to where the data is stored. So the transfer of data can happen very quickly. And then what you get back, sent back from Service X is only that data that you're going to really need for subsequent processing of your data. And that can actually speed things up very substantially. So if you're running on a slow internet connection and you're running this whole thing locally, for example, then you will see that that first stage, this type of processing can take forever. So I can tell you for reference, on a slow internet connection that I had a few days ago, this takes about 10 minutes. And this pattern that we're showing you now takes a few seconds in comparison because the amount of data is going to be drastically reduced. So let's take a look at how this works. We're going to first set up our query. This uses funcadl. There was not a contribution about this at this workshop, but there was one at PyHEP 2021 if you want to take a look. The query that we have here is actually quite simple. We're not making any kind of event selection. We're only saying these are the different columns that we want. So if you look back at our input files, those are all branches in that file. And those are all the branches that we want to use. So the query here says, look at that file and select all of the columns that match those names, and please return them to us. So that is the request that we have. We then need to send that request off so that it can actually get processed. There's one small hack here. Don't worry about it. Read the details here if you're curious. This is only for demonstration purposes to reduce the amount of code here. We're going to need a different base class for the processor that we defined above, but otherwise the processor is the exact same. So our workflow will look the same other than this like tiny change here. So it's essentially the same type of setup we had above. And now, which means we're going to start this by sending to Service X the request, please process this data. We're getting the request back. And as the data comes back asynchronously, Coffee will start picking up the data that is coming back and start processing it. And once everything is done, it will return us again this object with all the different histograms inside. Now, what you'll notice up here is that we're generating a unique name. So if you're following along, you will also generate a unique name now. And the reason for this, you'll see in a second, because as I launch this, we get a unique name now, Sweet Sidewinder. And you can see multiple progress bars appearing for all the different processes that we care about. And there's two of these process bars per process. The first one is going to be the processing of that data. So like service X actually doing the data processing. And the second one is then us downloading that data again to the place on which we're running. I'm switching over to the dashboard now here, where we can see the progress of service X, and I'm going to update it. You'll see here some earlier runs that I did, and they all have names associated to them. And the reason that I give everyone a unique name is that if you're running and you're also following along now, you will also start appearing here. And I want to identify which one I am, and like you can see your unique name. So that's why everyone here has a unique name. So you see here the different things here that are called Sweet Sidewinder. This is everything that I just launched, because that's my name that was assigned for me. You can see the progress of these different tasks, and you can see we're already quite far advanced with most of them. The first ones here have already finished. Many of the files are completed. You can see they're processed by multiple workers in parallel. So here we can really also scale. If we have a large amount of data that needs to be processed, then Service X is executing this for us at scale. This is now running at the University of Chicago, this instance of Service X that is doing the data processing. And if we switch back to our notebook, you can see that the processing is happening, but also the downloading is happening, and we're fully done now here in about 100 seconds. We talked to Service X sent us back the data, and then Coffee processed this data. And we're using still DAS because we have it enabled, and you can see now looking at the stream up here, the different jobs that process these data. There's lots of gaps here because ultimately we're waiting on the data to arrive back. And then once the data is there, the processing is actually very fast because there's not a lot left to do. And that's why there's some gaps in here. But Dask has now also processed all of the data, and we're fully done. So we got back this object called all histograms, and then we gave it a new suffix here, Service X. And the reason I gave it the suffix is to now show you that we actually get the same thing. And that's in this next cell down here, which I can run. And you'll see that nothing happens in this cell. That might be a bit underwhelming. So let me just add another type of printout here, which is going to say that everything agrees. And what this does is it loops over all the different axes in our histogram, over all the different dimensions, and it checks whether the two histograms reproduced, those we produce with Service X and those we produce just with plain coffee, are in agreement. And indeed, you can see they are all in agreement. We get the same data out of it, which you would expect, right? We're doing the same type of data processing. We're just using a different pipeline where we have this additional Service X instance running in front, which can help us run things more efficiently. If you look at it in detail, you will see that we're skipping one specific variation here. That's due to technical reasons. One of the systematic variations that I showed you up there was computed, including random numbers. We're currently not fixing the seed to get some deterministic outcome here. So these histograms are by design varying every time that you run them. So it doesn't make sense to continue this variation, but everything else here is in good agreement. So everything here looks good. All right, and then with this, I'm at the end of the demonstration. I want to say a few last things here about what's next for this project. And the first thing here, as I was already alluding to on the slides, is to add more features here. Machine learning is something that has been requested, and that we also would like to add to this demonstration because it's quite relevant to people running physics analysis. There's typically machine learning components in there nowadays, so we would like to get this added to the setup. And what we're moving to next now, actually, and what we're working towards for another conference, ACAD, happening next month, is benchmarking the performance of all the different pieces in this workflow, and then subsequently also addressing bottlenecks that we're identifying. So we've already been working on this a bit, and we found things and we addressed things that can help improve the performance of this pipeline, and we will keep working on that. We're also very interested in seeing different implementations of this analysis task. And I think there's a lot to learn if you can have one type of benchmark analysis that you approach from different angles with different implementations, and you see how they compare, what the usability is like, and everyone might have different preferences of like how they approach something. And I think it's interesting to see this, to exchange ideas. and to potentially find better solutions that then also might translate to other types of implementations. There's a root R data frame based implementation you can find linked here. There's also a partial implementation we have that's written in Julia. You're very welcome to check them out if you're interested in that. And if you have additional implementations you're curious about that you would like to give a try, they're very welcome. In this repository here, there's also a plain text description of what this analysis task is, what it all includes, which might be useful. So you can work against that when you write something instead of having to work against the code here. That's sort of the reference implementation for this analysis task. And then lastly, a goal really here is also collaborating. And what that means is if you really have anything connected to this where you're like, oh, I would be interested in looking at this kind of aspect or adding this type of feature or investigating something, then please do get in touch, because we hope that this can be a project that can be useful to the community. And I think it can be in many ways. If you have any type of software libraries that you're working with, that you're developing, that you might want to test in practice, and that you might want to test on public data so that you can actually also easily show them off without being restricted by the requirements that the different experiments have at the LHC, then this might be a good use case. If you're working on analysis facilities and you might want to benchmark physics analyses, you could use this as well. And maybe you're just curious about how you might want to do analysis at the high luminosity LHC. So please do get in touch. Again, there's a link to the mailing list down here. And there's also a link to the main repository that we're using. This demonstration today was based on earlier work that we did and another workshop we had run. And there's more information, more links in this repository. So please feel free to check them out if you're interested. And with that, that's everything I've had. And I see now there's a question. So let me take a look at that. And then if there's anything else, I'm happy to address them. All right, the question is, how large of a cluster do you want to run the final demonstration on? This was 10 workers with 1 terabyte, so 4,000 workers with 400 terabytes. All right, so I think there's two pieces to this. So there's the one question, which is, what kind of cluster would I like? And the answer to this is essentially like as large of a cluster as I can get. And the other piece is sort of, what do you envision that people will actually realistically have in the future, right? So I guess the answer to the first one is we're going to work on all the facilities that we can run on. So we're working together with the operations programs US Atlas and US CMS, and there's various facilities in the US that we're all trying to get this set up. On multiple of them, we're already running this. So realistically, there you're going to get hundreds and ideally thousands of cores that you can run on in parallel, because really one of the goals here is to see, is it realistic to have this kind of interactive analysis workflow where you start this notebook and you're done within a few minutes with all of the different pieces that are done. And one thing actually I didn't show, let me run it now in parallel while I'm answering questions, is that one thing that's crucial for interactivity and for fast turnaround is caching. If I run this thing up here again, which took 100 seconds before, let's see how long it takes this time, because it's going to be much faster. And the reason it's going to be much faster this time is because all of the data is cached that we used previously. So this time, when we run this a second time, and you can try this on Binder as well, you're not actually going to run service X again, because all of the data is already there, so you only need to run the coffee step. So this type of thing, this sort of caching, you see now it's 25 seconds, it was 100 before, is crucial if you want to really be interactive. Okay, and another question from Matthew. You already did a bit, but can you talk more about the coffee cluster deployments at different analysis facilities and who can access them? Okay, right. I don't have slides for this, but I think we probably have slides in the introduction from the last workshop. So if you go here, the workshops are linked, and there might be you might be able to access it from there. This information. So we do have one facility, the one actually that I'm running on at the University of Nebraska-Lincoln, that is open, where you don't need to be on a specific experiment in order to access it. And you could get there with your CERN credentials. There's other facilities in the US specifically, where I'm most familiar with them, that are then typically restricted to either CMS or Atlas. And you can, again, depending on the facility, log in via different methods, for example, with your CERN credentials. So for example, at Chicago, there is an Atlas instance. a Coffee Casa instance that's available to you. Then at Nebraska, there is another CMS instance, also Coffee Casa instance that's available to you. And then there's various other instances throughout the US at Fermilab, at BNL, at MIT, various facilities where you do need then specific credentials in order to get access there. If you're curious, though, I can look up the link. I can send the links in Slack so that the people who would like to check out the facilities can find where to go in order to get access. Okay.
Okay. I think we're at time, but thank you, Alex. That was a hugely impressive demonstration. So that was excellent.
Thank you very much.
Thanks. Yeah, thanks so much for the work for that. And now to keep time, we're going to move on, and we'll be hearing about we'll be having a notebook talk length mini tutorial all about awkward and our data frame, which is also really interesting and important new work. So I'll let the next speaker take it away.
Thanks. Can you see the slides?
Yeah, very well.
Okay, great. So hi, I'm Jana Osborne. I'm a research software engineer with Princeton and PyHEP, and my background is in physics and computer science. And I work with Jim on awkward array, and this is our new development where I'm really pleased to present this connection of awkward and our data frame. So when we look at the awkward array and our data frame, they're two very different ways of performing calculations, large-scale calculations. And as Alex has shown just recently, just in previous talk, what we can do with awkward array is in a typical workflow, when you get columnar data served by service X or uproot, then you present users sees them as awkward arrays and does selection, event selection, applies systematics, so on and so forth, produces histograms and so forth. And the R data frame is a declarative analysis interface, and it actually reads from columnar data format via data source, and it supports many input formats. I'm not going to go into the details what those projects are. I'm sure that you, most of you know by now already what awkward array is, and except for those two things, they are quite different, but in a way that now we have the bridge that provides users with more flexibility in mixing those different packages and languages in their analysis. So there are numerous benefits in combining both C++ and Python, and let's try to do this on a small example where we take awkward arrays, put them in our data frame, perform some analysis there, and for users who actually do have preference for C++ root and analysis in our data frame, exporting those some data to awkward array can open multiple paths of using other tools in Python ecosystem. There were several talks I mentioned here. Links are available, which were presented at this workshop. And there will be two more tomorrow, Dax and Kush's, how awkward arrays are used with Dask and uproot. So let's start from awkward array to our data frame. This module is part of awkward array version 2, which is currently a submodule. So we import awkward array, and we need also root. Let's define a typical, very simple array of records and the array of lists, and just a flat array. So when we check the types of the arrays, we can see that they are variable length arrays for these records. for the list as well. And all those three arrays have the same length. So this is the requirement for the 2R data frame function, which is an awkward style function. So it takes a dictionary, and this dictionary has a key which will become the column in R data frame and the awkward array. So each key has to be unique. The lengths of all arrays have to be the same. So when we execute this function, we have a data frame, and we can actually look at the state by asking to describe itself and print the information. So we can see the columns. What are the columns? What are the column names? And what is the column type and the origin? So we put into the our data frame three arrays. So the origin is data set, and one column is defined, so don't worry about that. It's just used internally for filtering. And you can see that the record array has a very strange awkward type. It's kind of hashed because the awkward arrays are dynamically typed. And in fact, we don't need to know the type because we can use the placeholder type specifier auto. So we'll just get all the needed information when we actually use this records. And the list arrays actually are converted to RVEX, and you can see that this is the type which is native to our data frame. So I should mention that the data is not copied. The same information we can get from data frame about the column types, and it will return the strings of the array for the column types for X, Y, and Z. And now we can schedule some operations on our data frame. For example, we can ask the data frame to filter all columns on the column Y, where the values of this array are greater than 2. And let's check that the data frame didn't trigger the event loop, because this is something we want to avoid. It can be a very costly operation to run the event loop on all the data. So usually scheduling these operations doesn't trigger it, and we ask to describe and print again, and we can see that we have the same number of columns, and the event loop was not actually run. What can we do now with the data frame? Let's take some this data out as awkward arrays, and we provide the function from our data frame that can take selected columns and convert them to native awkward arrays. So this function takes a tuple of strings, which are the RDF column names, and the event loop, the RDF event loop, is triggered only once to retrieve all selected columns at once. So the result of it is, we can see it's an awkward array. And let's check the type, whether actually it was filtered. We also use the show with the parameter to show the type. And we can see that the type of this array, it contains records. This one is slightly weird because we put records with the field X in the column X. So we had 3 columns in our data frame which were retrieved, Y, Z, and X, and the types seem to be correct. And also, let's check the values that actually we did get them filtered with the Y greater than 2. And we print the results of the column Y, which is correct. And you can see that the other fields are also returned as filtered based on that, because So now we can actually check again. You know, this is what I'm getting obsessed with, the whether we run event loop or not. And the event loop was run only once. And so that's and the same information about the columns. So nothing changed there. For slightly deeper information about how the data is copied or not, you can look at the layout. This is usually something users will not do, but just to make sure that we actually had this record array with all the values, and you can see that the array which we took out of the R data frame still has all these values, but this record array is indexed. So we don't see the values which didn't match the selection, but the values are still there. However, if we look at the list of set array and flat array, we can see that the values were actually copied. So in this case, we lost the original information that this data came from the awkward array, and it became RVEC. So we actually copied them back. So we can do the same operation on awkward arrays in Python just to make sure that we get the correct results and check that the type is expected. So we can create an array of all these three arrays and filter it on the field on the record Y with the values greater than 2 and check the type. You can see that the type is exactly the same. However, if we look at the layout is different, because in this case, we didn't change any of the records at all. So the indexed, the values of the records were indexed at the very top. It's because the awkward arrays are actually immutable. So when we go from R data frame to awkward array, this function from our data frame converts selected columns to native awkward arrays. And the function takes a tuple of strings that columns and recognizes the following column types. So the primitive types, like integer, float, what you can see in this table in green. And so actually the Python types, you can see this in blue. When we have an array type of NumPy type of a primitive type, it will be translated into the vector of a primitive type, or actually we can have array type of a list type nested multiple times, and then NumPy type of primitive type. So this in C++, it will be converted to nested vectors or nested RVECs of these types. And all these types are supported except for datetime, time delta, and Boolean. Awkward types that are runtime generated, those are derived from awkward array view or awkward record view. They are not copied because awkward arrays are immutable. So let's try a small data analysis, and we'll go from C++ to Python. We'll take CMS open data for that contains some muon collection of NaN-IIDs. So this data set is called events in the file, and it contains number of muons in the event, transverse momentum, pseudo-rapidity, azimuth, mass, and charge of the muons. And let's see, we'll just give this file to the R data frame, and R data frame is capable of reading remote files, and in this case, it's my local file, and we can check the state of the data frame. So you can see all these columns were read from the data set. So we can have we have vectors of floats and integers, and number of muons as just an integer. And let's build a small analysis studying the invariant mass of this dimuon system. I put a link to the root tutorial for more information. And so for the our data frame, we can schedule some operations. They will not trigger the event loop, but we want to have the records with the columns with number of muons 2 with an opposite charge. We'll define the dimuon mass by applying the function which is also provided by root on those 4 columns, and then we filter again for dimuon mass of greater than 70 GeV, and we'll take only 1,000 records of that. So the event loop is triggered only when we actually ask the mean value of the dimuon mass. And this is something to remember. This is our baseline. We get the approximate mass of the Z boson of 91.44 GeV. And to make sure that the operation is triggered only once, we ask the data frame to describe itself, and we can see that the event loop is run only once. And now we can also see that we have additional column, dimuon mass, which was defined, which didn't come from the data set. How about we convert some selected columns to awkward array? So we've done all this analysis, and now we're interested in taking this dimuon mass column and do some maybe nice things in the Python world, like plotting, and maybe just continuing analysis with the other packages. So we, as we have seen that the scheduled analysis executed event loop only once, the user takes data out as an awkward array using from our data frame function. It selects dimuon months column, and we get awkward array, thousands lengths. We can look at the array type and see that it's just the bunch of floats, and this is something we want to check again, that the event loop was run one more time. So we have run the event loop twice, one for analysis and one for taking the data out as awkward array. Then now we have data as awkward arrays in Python, and what we can do with them, Alexander, you can see Alexander's talk or James' talk, and in this tutorial we just plot those with the hist, and we can see a nice distribution. Or we can just say, okay, let's double check and use it NumPy and check the mean of this dimuon mass, which is exactly the same number as we got before with the analysis on the R data frame with the root function. Now we'll try to do a round trip, and we will use the same file, which is about 60 million events. And in principle, we can enable the multi-threading with the, this enable implicit multi-threading. And then we'll just take all of the events as awkward array, and we'll take all the columns which are in this file. We can see that we have the awkward array of about 60 million records. And the type of this awkward array has all these jagged records, and you can see that some of them have 2 muons, some of them have 1 and 4, all this variation. So what can we do with that? Let's put it back in our data frame. And we'll just put it back as a single column, events. And it doesn't take much time whatsoever. And when we check the data frame, we can see that the event loop was not run. And we have the column, which comes from the data set, and it's awkward type, which is a record. So how do we deal with this column now? Because we know that this type is awkward record, but we want to access actually the records of this, the fields of this record. So we can use the functions, which is the function is exactly the same as the function's name is the same as the field name of the original record array. So if we look what were the fields of this array, now we can access the data from this column as events, as we put as a column events, column name, and the field record field name. And those functions will return an iterable object. In fact, it's going to be rvec, and an integer index can be used to access the elements of the records. Like, for example, here, when we want to have a muon charge of the first muon. And the same invariant mass C++ function can be applied to define a new dimuon mass column. So we can see that we'll do the same. We'll do the same selection. We'll want to have two muons. We want to have muons of opposite charge, and we define the new column of dimuon mass with the invariant mass function, which comes from root, and the parameters of this function, the arguments are going to be the records of the awkward array, which is in our data frame. So we'll take muon pt, muon eta, phi, and mass. And finally, we'll just say we want to have dimuon mass, which is greater than 70, and a range of only 1,000 records. So we schedule this analysis. The event checking again the event loop run only once, and we have now new column which came from define, and when we ask to print it, we get exactly the same number, 91.44 GeV. Okay, so now we know how to use awkward arrays in our data frame. Let's define our own invariant mass function that takes an awkward type. And we can actually write a lambda function and give it to the define. So in this case, I'm doing the same pre-selection, just using the same. We could put the if statements here in the code, but it's going to be less efficient. And you can try it in your environment. You can try to run the notebook yourself and check whether it makes difference. And I bet that our data frame will filter. It's much faster than even the C++ code which you provide. So in this case, we scheduled the analysis with our own lambda function. We asked the data frame to describe itself, and the event loop ran only once. We have this dimuon mass column now, which we just defined. And when we ask for the mean, we get exactly the same 9144 GeV. So in this case, I didn't filter post-defined, so I had to add the filter on diameter mass greater than 70, and also take the range of 1000, because actually in this case we have 60 million records. Let's check that the result is actually the same by taking out the diameter mass from the R data frame as awkward array, and we get this result. And we check, we select again that we want to have only those which are greater than 70 GeV, and calculate the mean using NumPy, which gives us exactly the same result, 91.44. We can go even further and define C++ functions. You can do it either like here in your code or in the header file. This is pretty much, you can recognize it's a copy of the function which root provides with slight variations that we can define, say, use different type. In this case, we schedule, the only sort of downside is that you can only define a function once. So if you put this function, if you define this function and then you just say, okay, but now I have to change something and I want to do modify the body, you would need to rename it, and because when we give it to the interpreter here, to the compiler, it puts it in the global namespace, so it's just a slight downside of that. Nevertheless, we can apply the same analysis to the data frame now with your own defined function. And you can see that, as I said before, the records are actually recognized as RVEX. And we schedule the analysis and we ask for the mean value and we get exactly the same result. So if we if this is slightly awkward, you may want to say, okay, I don't want to have awkward types in my R data frame. In this case, you can place the records as native RVEX. And for that, we just ask awkward array to provide us single records, and then we place them as different columns in the data frame. Again, after we put it into the data frame, we can check, and now we can see that the columns are actually native RVEX. And after that, you can also apply the same function on RVEX and get exactly the same result. So in summary, awkward arrays and R data frame provide two very different ways of performing large-scale calculations. And I hope that you will benefit from using both of them. And this awkward RDF bridge actually is part of version 2, which is currently a submodule. And the awkward version 2 will be released at the beginning of December 2020. If you want to see the timeline, it's here. And your feedback is greatly appreciated. Please report issues and ask for any features if you feel that it's something is missing. Thank you very much. So now I can take questions if there are any.
All right, thanks. That was a really cool talk. I think we have about time for one question. I'm looking at Slido now and I don't actively see any. So maybe we can just try and solicit questions from the room. Okay, I've not seen any. I'm assuming we are kind of tight on time, so I will maybe say that I can ask my question and a few other ones as they come up in Slack. So thanks again for this this nice talk. I thought it was pretty cool to be able to see these two interact. And then we're going to move on to our final kind of talk for the day before we get to the hackathon. So we'll be hearing now from Derek on developing implicitly parallel Python analysis tools for Nova.
Okay, can you see me and hear me and see my slides?
Yeah, they're not in full screen, but I think that's fine. Okay, now they are.
How's that? Great.
Yeah, excellent.
Awesome. All right, well, hello everyone. I'll be presenting some implicitly parallel analysis tools that we've been developing as part of the DOE-sponsored SciDec4 program together with the Nova experiment. So as you know, high-energy physics experiments collect massive amounts of data, which is a feature of our high-intensity beams. The problem can quickly become intractable, though, as event structure complication rises and as we develop detector technologies with finer resolutions, like in the case of the liquid argon time projection chamber. The first step of many of these analyses performed by these experiments is to filter through the data to extract the features that they want to analyze. Since each event can be processed independently, this task is easily made parallel. And so far in this conference, we've heard from a number of frameworks that are designed to do just this. I'll present our analysis ecosystem, which leverages high-speed interconnect and data storage and delivery capabilities of high-performance computing platforms. And I'll also show an example analysis from the Nova neutrino oscillation experiment. And although what I'll show you is in the context of neutrino physics, the framework is designed to be experiment and domain agnostic in order to support all types of columnar data analysis. So first off, the foundation of our analysis ecosystem is HDF5, which allows us to take advantage of the native and highly scalable parallel I/O and compression features of the format, as well as the highly optimized MPI implementations provided at HPC facilities. HDF5 also boasts a large investment from industry players. And so as the format grows, we're able to sort of piggyback off of those developments. So we've designed a schema for efficient columnar analyses in HDF5. Here, the deeply nested n-tuples that we're used to are flattened into separate tables. And then the elements of those n-tuples within each table are stored and directly read in columns. In the language of HDF5, these are groups and data sets respectively. And so here, each row in each table are indexed by event number and some additional run information in order to associate event features across tables and to support irregular table sizes within a single file or within a single analysis. For example, each of these T-tree branches that I have in the left here would become a separate HDF5 group. And the leaves of those branches become data sets within the group or columns within those tables. Then using the run information, we can associate the neutrino energy like I have here with some information in, say, the spill group that's held in a separate table. HDF5 I/O is performed by chunk and supports partial reading of data sets as they're needed. This allows us to analyze files of arbitrary scale without adding overhead to many parallel processes reading smaller portions of the data. So we've looked at how we can benefit from concatenating many of our HDF5 files into smaller and smaller number of larger files using some software that was developed by collaborators at Northwestern University. Here we demonstrate scaling event selection time as we concatenate an entire Nova Monte Carlo dataset into fewer and fewer files. We find that a single monolithic file provides the most flexibility in terms of analysis configuration with a consistent 10 times speed up compared to similar analysis on the equivalent individual files that make up the monolith. It was made using only 985 CPU hours on the Nurse Cori system. With that, it compressed 3 terabytes of uncompressed data down to about 280 gigabytes, which at that point is suitable for laptop analyses as well. We've also developed a Python-based event selection framework that we call Pandana to sift through this HDF5 organization. Pandana implements implicit parallelism using the event indexing that I mentioned earlier in order to distribute the workload among different MPI processes running a single job, all without the user needing to intervene to code any of that up. This leverages HDF5's parallel chunk-based I/O, and again can handle irregular group sizes. Users in this framework write Pandana cuts in vars, like in these examples they have in the bottom left or bottom right. These cuts and vars accept Pandana tables, which essentially is a proxy for HDF5 groups, and they return the tables return pandas data frames as a result from reading the data. And so here, by requesting this rec.vertex.elastic group, the data is read and returned into a real pandas data frame, which at that point the user can perform arbitrary operations on the data, pandas or otherwise. Also, these operations can be as simple as one-liners, like I have in the neutrino energy variable down at the bottom, but can also be something much more complicated, like this fiducial volume cut. Some potential improvements in this framework that can be made are reducing the number of redundant and superfluous event indexing information that's read in order to match the events across different groups, but also general improvements in the overall data flow using something like an abstract syntax tree. We're also developing an implicitly parallel histogram package that we call Llama, just to stick with the animal theme. It wraps boost histogram for performance and feeds from the pandas data frames returned by Pandana. Reduction operations here are performed lazily for common histogram operations based on the arithmetic properties of those operations, which you can see illustrated in this flowchart. Here, each process has its own copy of histograms H1 and H2, and when the user wants to sum these into H3, the results aren't collected from all the processes until they're needed. They need the aggregate result at serialization time. Additionally, these histograms implement the unified histogram interface for easy plotting with other tools like PyHEP. So to show a complete workflow, I present here an analysis of realistic scale, which is a measurement of the electron antineutrino charged current cross-section in the Nova near detector. We analyzed multiple samples of Monte Carlo, which in total contains almost 200 million slices in time and space. These are held in about 600 gigabytes of 4 of those monolithic HDF5 files. The number of unique HDF5 groups and data sets accessed within each file are 16 and 54 respectively, just to give you a sense of the complication or the complexity of this analysis. And then finally, using NERSC's new Perlmutter system, we achieve near perfect scaling with a total processing time on the order of minutes, which really enables us to do real-time exploration of the data at this scale. So this example illustrates, again, an implicitly parallel Python analysis workflow in the context of neutrino experiments. But as I said earlier, these tools are well suited for any columnar data analysis. So if any of this interests you, please feel free to watch the repos that I linked in this talk or to reach out to the team. Thanks.
Okay, thanks very much for this nice talk. So we have a little bit of time, and we have one question on Slido. Are local analyses on laptops common in your field? I have rarely dealt with more than 1 gigabyte of files locally before moving elsewhere, but this particular question asker is coming from Atlas.
Okay, yeah, they're not so common in our field just because the data sets that we have are typically pretty massive. And so this sort of, enables a completely new workflow that might be completely contained on your laptop. But as of now, it's not super common in neutrino physics, as far as I know.
Okay. Okay, and so it doesn't seem like we have any other questions on Slido. I'll go ahead and ask. So for your Llama library on slide 6 that you said is basically like an extension of Boost Histogram. Is the work that you're doing there to make it to add the parallelization, is that something that, excuse me, is that something that is big enough deviation from what's currently done in Boost Histogram that it needs to kind of stay its own library or stay as its own library, or is this something that you think there might be able to be contributions back towards the upstream library?
Right. So I'm not super familiar with the inner workings of Boost. I know it's a pretty large library, but yeah, these operations are relatively simple, I would say. And so it would be interesting to explore adding that into Boost. But for the purpose of this study or workflow, this is we sort of decided just to build upon that for now.
Yeah. Okay, great. So thanks very much. Let me make sure that we don't have any. Yep. Okay. So no other talks. So let's thank Derek again. That was great. And so now that's the end of our formal talks for today. But we'll be back in just under 20 minutes with an introductory talk from Amin about basically what this hackathon is that we're going to be doing over the next few days. So thanks everyone for joining. We'll see you tomorrow, and we'll also hopefully see you back here in just about 20 minutes.